Where do most of the ocean's fish live? Not in the sunlit waters, but in the Twilight Zone below, where the mass of fish exceeds all human fisheries combined. Allow your breathing to slow as the gentle sounds begin, and let your body sink into the quiet. We are going somewhere. There is time. There is. The lights can stay dim. This hidden realm between 200 and 1,000 meters deep receives only 1% of the sun's light, yet it holds the largest animal migration on Earth. Every day, trillions of creatures rise from the depths to feed at night and sink back before dawn, a journey almost no one has ever witnessed. Beneath the surface of the ocean, where the last remnants of daylight fade, a vast and mysterious realm begins. This is the mesopelagic zone, a region of water stretching from 200 meters down to 1,000 meters below the sea surface. It is a world defined by the physics of light and the optics of water, where the very nature of visibility changes with every meter of descent. The sun, that great engine of the surface world, sends its energy downward, but the ocean absorbs and scatters this light with ruthless efficiency. By the time we reach the upper boundary of the mesopelagic zone, at 200 meters, only 1% of the sunlight that struck the sea surface remains. Below that point, the light continues to diminish exponentially until at 1,000 meters, no sunlight penetrates at all. This is not a mere darkness. It is a total absence of solar photons, a place where the only light comes from living creatures themselves. The attenuation of sunlight through seawater is a complex process governed by the physical properties of water molecules and the particles suspended within them. As sunlight enters the ocean, its photons interact with water molecules, which absorb and scatter the energy. The rate of attenuation is not uniform across all wavelengths. Instead, each color of light is absorbed at a different depth. Red light, with its longer wavelength, is absorbed within the first few meters of the surface. Orange and yellow follow soon after, typically disappearing by 50 meters. Green light penetrates deeper, but it is the blue wavelengths, with their shorter wavelengths and higher energy, that travel the farthest through the water column. In the clearest ocean waters, blue light can reach depths of several hundred meters, though its intensity is drastically reduced. This is why the mesopelagic zone appears as a deep blue twilight, even at 200 meters, where the remaining 1% of sunlight is almost entirely composed of blue and green wavelengths. The optical physics of this zone are such that the human eye, adapted for surface light, would perceive only a dim, monochromatic blue glow at the upper boundary. Below 400 meters, that glow fades to an almost imperceptible level, and by 600 meters, the human eye would register no light at all, even though some photons may still be present. The depth at which light becomes undetectable to the human eye is known as the compensation depth, but in the mesopelagic zone, the concept of light is more nuanced. Photons of blue light can exist at depths of up to 800 meters in exceptionally clear tropical waters, but their intensity is so low that they are measured in terms of single photons per square centimeter per second. This is a regime of photon counting where the distinction between light and darkness is not binary but probabilistic. The eyes of animals that inhabit this zone have evolved to be exquisitely sensitive to these faint blue wavelengths, often with specialized photopigments that peak in absorption at around 480 nanometers. This wavelength corresponds to the peak transmission of blue light through clear ocean water, a coincidence that is no accident of evolution. The physics of light attenuation thus dictates the visual ecology of the entire mesopelagic realm, shaping how creatures see, hunt, and hide. Beyond the behavior of light, the mesopelagic zone is also defined by its physical structure, particularly the presence of strong gradients in temperature and salinity. The thermocline is a layer of rapid temperature change that typically occurs within the upper part of the mesopelagic zone, often between 200 and 400 meters. In most oceans, the surface waters are warm, heated by the sun, but as one descends through the thermocline, the temperature drops sharply, sometimes by 10 degrees Celsius or more over 100 meters. This thermal gradient is a stable feature of the ocean, caused by the fact that warm water is less dense than cold water, and the two layers resist mixing. The thermocline acts as a barrier to vertical mixing, trapping heat in the surface layer and keeping the mesopelagic waters cold and dense. Below the thermocline, the temperature continues to decrease but at a much slower rate, reaching a few degrees above freezing at 1,000 meters, depending on latitude and oceanographic conditions. In the tropics, the deep mesopelagic waters may be around 4 to 5 degrees Celsius, while in polar regions they can be near freezing. Closely related to the thermocline is the halocline, a layer where salinity changes rapidly with depth. Salinity, the concentration of dissolved salts in seawater, also affects density, and the halocline often coincides with the thermocline in the upper mesopelagic zone. In many ocean regions, surface waters are fresher due to rainfall and river runoff, while deeper waters are saltier. The combination of temperature and salinity creates a pycnocline, a layer of sharp density increase that is one of the most important physical features of the ocean. The pycnocline in the mesopelagic zone is so strong that it resists vertical mixing, isolating the deep ocean from the surface. This density stratification has profound implications for the transport of nutrients, dissolved gases, and even sound. The pycnocline acts as a sound channel, where sound waves can travel for thousands of kilometers with little attenuation, a phenomenon known as the deep sound channel or SOFAR channel, which often lies within the mesopelagic zone. The oxygen minimum zone, or OMZ, is another critical physical feature of the mesopelagic zone. Typically found between 200 and 800 meters depth, this is a region where the concentration of dissolved oxygen in the water is extremely low, sometimes less than 1 milligram per liter. The formation of the OMZ is a direct consequence of the physics of the zone. Surface waters are rich in oxygen because they are in contact with the atmosphere and because photosynthesis by phytoplankton produces oxygen. As organic matter sinks from the surface into the mesopelagic zone, it is consumed by bacteria and other microorganisms in a process called respiration, which consumes oxygen. The thermocline and pycnocline prevent the vertical mixing that would bring oxygen-rich surface waters down to replenish the deep layers. At the same time, the slow circulation of deep water means that oxygen is used up faster than it can be replaced. The result is a layer of water with very low oxygen, sometimes approaching anoxic conditions. The OMZ is not uniform across the globe. It is most pronounced in the eastern tropical Pacific, the Arabian Sea, and the Bay of Bengal, where upwelling and high productivity create a large demand for oxygen. In these regions, the core of the OMZ can have oxygen levels so low that most fish and invertebrates cannot survive, creating a vertical barrier that many animals must cross during their daily migrations. Water pressure is perhaps the most relentless physical factor in the mesopelagic zone. At the surface, pressure is 1 atmosphere, the weight of the air above us. For every 10 meters of depth in seawater, pressure increases by approximately 1 atmosphere. At 200 meters, the pressure is 21 atmospheres, over 300 pounds per square inch. At 1,000 meters, the pressure is 101 atmospheres, or about 1,450 pounds per square inch. This immense pressure has profound effects on the physics of the zone. Gases compress under pressure, so any air-filled spaces in organisms must be adapted or absent. The pressure also affects the structure of water molecules themselves, making water slightly more compressible than at the surface, though still nearly incompressible compared to gases. The pressure gradient is linear and predictable, but it represents a massive force that any creature living in the mesopelagic zone must withstand. The physics of pressure also influences the behavior of sound, as the speed of sound in water increases with pressure, temperature, and salinity. The sound speed profile in the mesopelagic zone is complex, with a minimum often occurring at the depth of the thermocline, creating the conditions for the deep sound channel. The temperature gradient in the mesopelagic zone is not only a matter of decreasing temperature with depth, but also of stability. In the upper part of the zone, from 200 to 400 meters, the temperature drops rapidly, often by several degrees per 10 meters. This is the main thermocline, and it is one of the most stable features of the ocean, persisting year after year. Below the thermocline, in the lower mesopelagic zone from 400 to 1,000 meters, the temperature continues to decrease but at a much slower rate, typically less than 1 degree Celsius per 100 meters. The temperature at 1,000 meters is usually between 2 and 5 degrees Celsius, depending on latitude and water mass history. This cold, stable environment is a constant in the mesopelagic zone, a world of perpetual chill that contrasts sharply with the warm surface waters above. The temperature gradient also affects the density of water, with cold water being denser, and this density stratification is the primary reason why the mesopelagic zone is so stable and resistant to mixing. Given the extreme conditions of light, pressure, temperature, and oxygen, it is remarkable that life exists in the mesopelagic zone at all. Yet it does, and one of the most striking adaptations to this dim world is the prevalence of bioluminescence. Bioluminescence is the production of light by living organisms through a chemical reaction involving luciferin and luciferase, often with the help of oxygen and energy from ATP. In the mesopelagic zone, an estimated 90% of all animals are capable of producing light. This is not a random occurrence, but a direct consequence of the optical physics of the zone. In the absence of sunlight, bioluminescence becomes the primary source of light for communication, predation, and defense. The wavelengths of bioluminescent light in the mesopelagic zone are predominantly blue-green, peaking around 470 to 490 nanometers. This is the same wavelength that penetrates deepest from the surface, and it is also the wavelength to which the eyes of mesopelagic animals are most sensitive. The physics of bioluminescence are thus intimately tied to the optics of the water column. The chemical reactions that produce light are highly efficient, converting chemical energy into light with minimal heat, a necessary adaptation in a cold environment where energy is scarce. The most sophisticated use of bioluminescence in the mesopelagic zone is counter-illumination camouflage, an optical illusion that relies on the physics of light attenuation. Many animals that live in the upper mesopelagic zone, where dim sunlight still penetrates from above, have evolved organs called photophores on their ventral surfaces, the side of their bodies facing downward. These photophores produce light that matches the intensity and wavelength of the downwelling sunlight. When viewed from below, the animal's silhouette is erased against the brighter background of the surface. This is a form of active camouflage, requiring the animal to constantly adjust its light output to match the changing light levels as it moves through the water column. The physics of this process are precise. The animal must measure the ambient light coming from above using its eyes or other light-sensitive organs, and then modulate the output of its photophores to produce an equal amount of light. The result is that the animal becomes effectively invisible to predators looking up from below. The optical physics of counter-illumination rely on the fact that the attenuation of light through water is a function of depth and wavelength. At 200 meters, the downwelling light is blue, dim, and directional. The animal's photophores must emit blue light at the same intensity as the background, which requires a sophisticated neural control system. The photophores themselves are often composed of multiple small light-emitting cells, each with its own lens and reflector, creating a dispersed light source that mimics the diffuse nature of the background light. This is not a simple on-off switch, but a continuous gradient of light output that can be adjusted in real time. The prevalence of counter-illumination in the mesopelagic zone is a testament to the selective pressure of visual predation. In this dim twilight, any creature that can reduce its visibility has a significant advantage. The physics of light scattering also play a role in this camouflage. As light passes through water, it is scattered by particles and water molecules, creating a diffuse glow that is not perfectly uniform. The photophores of counter-illuminating animals must match not only the intensity, but also the angular distribution of the background light. This is an extremely challenging optical problem, and the fact that so many species have independently evolved similar solutions underscores the importance of light in the mesopelagic zone. The physics of bioluminescence extend beyond camouflage to include communication, with many animals using specific patterns of light flashes to signal to mates or to warn off rivals. The patterns of these flashes, their timing, color, and intensity are all shaped by the optical properties of the water. The scattering of light limits the range at which these signals can be seen, typically to a few tens of meters in the clear waters of the mesopelagic zone. The oxygen minimum zone, while a chemical feature, also has a profound influence on the physics of the mesopelagic zone. The low oxygen levels affect the density and viscosity of water, albeit subtly. More importantly, the OMZ acts as a barrier to the vertical movement of animals, concentrating life in the upper and lower edges of the zone where oxygen is more abundant. The physics of gas exchange at the boundaries of the OMZ are complex, involving diffusion and advection. The lack of oxygen also affects the chemistry of bioluminescence, as the light-producing reaction requires oxygen. In the core of the OMZ, where oxygen levels are extremely low, bioluminescence may be reduced or altered. Some animals have adapted to this by producing light using alternative chemical pathways or by storing oxygen in specialized tissues. The OMZ is not a static feature. It expands and contracts with changes in ocean circulation and climate. The physics of the OMZ are tied to the global ocean conveyor belt, the large-scale circulation that moves water masses around the planet. The mesopelagic zone is a key part of this circulation, with water masses that have been isolated from the surface for decades or even centuries. The pressure at 1,000 meters is 100 times that at the surface, and this has a direct effect on the physical properties of water. Water becomes slightly more compressible under pressure, but its density increases by only a few percent over the entire depth of the mesopelagic zone. The compressibility of water is a factor in the speed of sound, which increases with pressure. The sound speed profile in the mesopelagic zone typically shows a minimum at the depth of the thermocline, where temperature drops rapidly and then increases again with depth as pressure dominates. This creates a sound channel that traps low-frequency sound waves, allowing them to travel vast distances. The physics of this channel are used by scientists to study ocean temperatures and by marine mammals to communicate. The mesopelagic zone is thus not a silent world. It is filled with the sounds of animals, the rumble of distant earthquakes, and the hum of human activity. The sound waves in this zone are affected by the same density gradients that affect light, but with different physics. Sound travels faster in denser, colder water, and the changes in sound speed with depth create a complex acoustic environment. The temperature gradient in the mesopelagic zone is not only a function of depth, but also of latitude and season. In the tropics, the thermocline is strong and shallow, often starting at around 100 meters. In temperate regions, the thermocline is deeper and weaker, and in polar regions, it may be absent altogether, with the water column being uniformly cold from surface to depth. The mesopelagic zone in polar regions is therefore much colder at the upper boundary, with temperatures near 0 degrees Celsius. The temperature gradient affects the density of water, and thus the stability of the water column. A strong thermocline inhibits vertical mixing, which in turn affects the distribution of oxygen, nutrients, and light. The physics of the thermocline are governed by the balance between solar heating and wind mixing. At the surface, wind and waves create a mixed layer of uniform temperature, but below this layer, the thermocline forms a sharp boundary. The depth of the thermocline varies seasonally, being deeper in winter when storms mix the water more vigorously. In the mesopelagic zone, the thermocline is a permanent feature, changing only on long timescales. The halocline, while less prominent than the thermocline in most of the mesopelagic zone, plays a critical role in the Arctic and Antarctic regions, where fresh water from melting ice can create a strong salinity gradient. In these regions, the halocline can be a barrier that prevents warm Atlantic water from reaching the surface, thus preserving the sea ice. The physics of the halocline are similar to those of the thermocline, but with salinity as the driving force for density. In the mesopelagic zone, the halocline is often found at depths where different water masses meet, such as the boundary between the North Atlantic deep water and the Antarctic intermediate water. These water masses are formed at the surface in different regions and then sink to depths where they spread horizontally. The mesopelagic zone is a crossroads for these water masses, and the halocline marks the boundaries between them. The density gradients created by the halocline affect the path of sound and the movement of particles and organisms. The optics of the mesopelagic zone are not only about the presence or absence of light, but also about the polarization of light. Sunlight becomes partially polarized when it scatters in the atmosphere and at the sea surface. Underwater, the polarization of light changes with depth and direction. Some animals in the mesopelagic zone have eyes that are sensitive to polarized light, using it as a navigational cue or to detect prey. The physics of polarization in seawater are complex, involving the alignment of water molecules and the scattering of light by particles. Polarized light can provide information about the direction of the sun, even when the sun itself is not visible, a valuable tool in the dim mesopelagic zone. The study of underwater polarization is still in its infancy, but it is clear that the physical properties of light in the mesopelagic zone are more nuanced than simple attenuation. The physics of the mesopelagic zone also include the phenomenon of submarine light fields, where the distribution of light changes with depth and angle. At the surface, light comes from above, but as it penetrates the water, it becomes more diffuse due to scattering. In the mesopelagic zone, the light field is highly directional, with most light coming from directly above. This is why counter-illumination is effective. The background light is brightest at the zenith and fades toward the horizon. The photophores on the ventral surface of animals must match this angular distribution to be effective. The physics of the light field are described by the radiative transfer equation, which accounts for absorption and scattering. In the mesopelagic zone, the scattering is primarily due to water molecules themselves, as the concentration of particles is low. This means that the light field is relatively stable and predictable, allowing animals to evolve precise counter-illumination strategies. The oxygen minimum zone, while a chemical feature, also has a physical expression in the form of density layers. The low oxygen water is often associated with specific water masses that have a distinct temperature and salinity signature. The physics of the OMZ are tied to the ocean's overturning circulation, which brings oxygen to the deep ocean. In the mesopelagic zone, the OMZ is a region where the oxygen consumption rate exceeds the supply rate. The shape and extent of the OMZ are controlled by the strength of the thermocline, the rate of organic matter sinking, and the circulation patterns. The OMZ is not a static feature. It can expand or contract over decades due to climate change. The physics of the OMZ are a key area of research, as changes in the OMZ could have profound effects on the mesopelagic ecosystem. The pressure at depth also affects the solubility of gases in water. At higher pressure, gases such as oxygen and carbon dioxide are more soluble. This means that the mesopelagic zone can hold more dissolved oxygen than surface waters, but the actual oxygen concentration is low because of consumption. The solubility of gases is a physical property that changes with pressure and temperature. In the mesopelagic zone, the high pressure increases the solubility of oxygen, but the low temperature also increases solubility. Despite these factors, the oxygen minimum zone persists because the rate of oxygen consumption by bacteria and animals is so high. The physics of gas solubility are important for understanding how the mesopelagic zone cycles carbon and other elements. The temperature gradient in the mesopelagic zone is also a factor in the formation of internal waves. These waves occur along the thermocline, caused by the interaction of tides with the ocean floor. Internal waves can be very large, tens of meters in height, and they propagate through the mesopelagic zone, mixing water and transporting energy. The physics of internal waves are complex, involving the Earth's rotation, the stratification of the water column, and the topography of the seafloor. In the mesopelagic zone, internal waves can create patches of turbulence that affect the distribution of plankton and the visibility of light. The study of internal waves is an active field of physical oceanography, and their role in the mesopelagic zone is only beginning to be understood. The mesopelagic zone is a world of physical extremes, where the laws of physics dictate the conditions for life. The attenuation of light, the gradients of temperature and salinity, the crushing pressure, and the depletion of oxygen all combine to create an environment unlike any other on Earth. The prevalence of bioluminescence and the sophistication of counter-illumination camouflage are direct responses to the optical physics of this zone. Every photon of light, every molecule of oxygen, every degree of temperature is a physical constraint that shapes the existence of the creatures that live here. The study of the mesopelagic zone is a study of physics in action, a testament to the power of the natural world to adapt to the most challenging conditions. The mesopelagic zone is a realm where the physics of light becomes a matter of quantum flux. Each photon of sunlight that reaches these depths has survived a journey through hundreds of meters of water, colliding with molecules and suspended particles along the way. The process of attenuation follows the Beer-Lambert law, which describes how the intensity of light decreases exponentially with depth. For pure water, the absorption coefficient is lowest for blue wavelengths around 475 nanometers, which is why the deep ocean appears blue. This narrow window of transmission defines the optical environment of the Twilight Zone, where the remaining light is monochromatic and directional. The water itself is not simply a neutral medium. It contains dissolved organic matter, often called CDOM, which absorbs ultraviolet and blue light more strongly. In coastal regions, where runoff brings terrestrial organic material, the mesopelagic zone may be darker at shallower depths than in the open ocean. The scattering of light by tiny particles, known as marine snow, also plays a role. These particles, composed of dead plankton, fecal pellets, and mineral dust, redirect photons in random directions. The result is a diffuse celestial glow overhead, while the view horizontally or downward quickly fades to absolute blackness. At depths approaching 500 meters, the downwelling irradiance is less than 1% of the surface value, and at 1,000 meters, sunlight is effectively absent. The concept of optical depth is central to understanding this environment. One optical depth is the distance over which the intensity of a collimated beam of light falls to 1 e, or about 37% of its original value. In clear ocean water, one optical depth is roughly 15 to 20 meters for blue light. The mesopelagic zone spans many optical depths, creating a gradient where even the most sensitive human eye would detect nothing beyond a few tens of meters. Yet the creatures that live here have evolved visual systems that can capture single photons. Their retinas are packed with rod cells, which are far more sensitive than the cone cells used for color vision. These rods contain a pigment called rhodopsin, which is maximally sensitive to the blue wavelengths that dominate the twilight. The physics of bioluminescence introduces a new source of light in this dim world. Bioluminescence is a form of chemiluminescence, where a chemical reaction produces light without heat. The reaction typically involves a molecule called luciferin, an enzyme called luciferase, and oxygen, along with adenosine triphosphate as an energy source. The emitted light is almost always in the blue-green range, with a peak wavelength around 480 nanometers, because this light travels farthest in seawater. The efficiency of this reaction is remarkable. Nearly 100% of the chemical energy is converted into light, compared to the roughly 10% efficiency of an incandescent bulb. This high efficiency is essential for animals that must conserve energy in the nutrient-poor mesopelagic zone. The spatial and temporal characteristics of bioluminescence are governed by the physical properties of the photophores, the light-producing organs. Photophores are often equipped with a lens, a reflector, and a pigment layer that directs the light forward or downward. The reflector may be composed of guanine crystals, which are highly reflective and can be arranged in thin layers to produce constructive interference. This creates a bright directional beam that can be aimed precisely. The timing of the flash is controlled by nerves that trigger the release of luciferin or the opening of a shutter. Some species can produce a steady glow, while others emit rapid pulses that may confuse predators or attract mates. Counter-illumination is a direct application of optical physics to survival. Animals that swim in the upper mesopelagic zone, where some sunlight still penetrates, face the problem of being seen as a dark silhouette against the brighter surface. To counteract this, many species have photophores on their ventral side that emit light matching the intensity and color of the downwelling sunlight. The physics of this matching is precise. The animal must adjust its ventral glow to the ambient light level, which changes with depth, time of day, and cloud cover. Some fish, such as the hatchetfish, have a highly reflective silver belly that acts as a mirror, reflecting the downwelling light and making them nearly invisible. The mirror is composed of multiple layers of guanine crystals, each layer a fraction of a wavelength thick, creating a reflective surface that is 95% efficient at the relevant angles. The optics of vision in the mesopelagic zone are also shaped by the physics of light transmission. Many predators have large tubular eyes that point upward, maximizing the capture of downwelling light. The lens is often spherical and large, with a short focal length, which increases the brightness of the image. The retina is densely packed with rod cells, and the eye may contain a tapetum lucidum, a reflective layer behind the retina that bounces light back through the rods, giving the cells a second chance to absorb photons. This adaptation is common in deep-sea fishes and contributes to their characteristic glowing eyes when illuminated by a submersible's light. However, the trade-off is a loss of resolution. The eye sacrifices fine detail for extreme sensitivity. The physics of contrast and veiling light further complicates vision. In the mesopelagic zone, the background light from the surface is not uniform. It is brightest directly overhead and fades toward the horizon. This creates a natural gradient that predators can use to detect the silhouettes of prey. But the prey themselves have evolved transparency or mirror-like surfaces to break up this silhouette. The physics of transparency requires that the body has the same refractive index as seawater, which is approximately 1.34. Many gelatinous organisms, such as jellyfish and salps, achieve this by having a body composed mostly of water, with thin, distributed cells. The refractive index of their tissues is very close to that of the surrounding water, so light passes through with minimal scattering. This makes them nearly invisible to both predators and prey. The optical properties of the water itself change with depth due to the pressure and temperature gradients. At greater depths, the water is colder and denser, which slightly alters the refractive index. However, this change is minute and has little effect on the propagation of light. A more significant physical factor is the presence of the thermocline, the boundary between warmer surface water and colder deep water. The thermocline can act as a weak lens, bending light rays slightly as they pass through the density gradient. But in practice, the effect is negligible compared to the massive attenuation from absorption and scattering. The most important physical constraint remains the exponential decay of sunlight, which defines the boundaries of the mesopelagic zone. The study of light in the mesopelagic zone also involves the measurement of radiometric quantities such as downwelling irradiance, upwelling radiance, and scalar irradiance. These measurements are made using specialized instruments deployed from research vessels. The data reveal that the spectral composition of light changes with depth. At the surface, sunlight is a broad spectrum, but as it penetrates, the red and yellow wavelengths are absorbed first. By 100 meters, only blue and green light remain. By 300 meters, the light is virtually monochromatic blue. This narrow bandwidth has profound implications for color vision. Most mesopelagic animals are monochromatic, possessing only one type of visual pigment. They cannot distinguish colors, but they do not need to, because the world is already a single hue. The physics of bioluminescence also includes the phenomenon of polarization. Some deep-sea animals, such as certain squid and shrimp, produce light that is partially polarized. The orientation of the polarization may be used for communication or for reducing glare. However, the ability to detect polarization is rare in the mesopelagic zone, and the role of this property is still an active area of research. More well-documented is the use of fluorescent proteins, which absorb ultraviolet or blue light and re-emit it at longer wavelengths. Some corals and jellyfish in the mesopelagic zone display green or red fluorescence, but the function remains unclear. It may serve as a type of camouflage or as a signal to other animals that can see fluorescence. The physical constraints of the mesopelagic zone extend beyond light. The pressure increases by approximately 1 atmosphere every 10 meters of depth. At 500 meters, the pressure is 50 times that at the surface. This pressure affects the density of water and the behavior of gases, but it has a more direct effect on the structure of proteins and cell membranes. However, the focus on physics and optics keeps us with light. The visibility of bioluminescent flashes is also governed by the optical properties of the water. A bright flash from a single photophore can be seen from several meters away, but the distance is limited by scattering and absorption. The flash must be intense enough to create a detectable signal before it is lost in the background. The mesopelagic zone is a world of optical extremes, where the darkness is punctuated by brief, precise flashes of light. The physics of these flashes involves the release of energy in a matter of milliseconds. The flash duration is controlled by the kinetics of the luciferin-luciferase reaction, and the intensity can be modulated by the number of photophores activated. Some species produce a prolonged glow, while others emit a rapid series of pulses. The pattern of the flash is often species-specific, allowing individuals to recognize each other in the darkness. This is a form of optical communication that relies on the physics of light propagation in a scattering medium. The study of the mesopelagic zone's physics is a young field with many unknowns. The optical properties of the water are not uniform. They vary with the concentration of plankton, the amount of suspended sediment, and the presence of dissolved organic matter. The biological pump, which transports carbon from the surface to the deep, also affects the optical environment by introducing particles that scatter light. The interaction between biology and physics is intimate, with each influencing the other. The creatures of the mesopelagic zone are not just adapted to the physical conditions, they are part of the system that creates those conditions. The bioluminescence they produce is a source of light that would not exist otherwise, and the particles they excrete change the optical properties of the water. The physics of the mesopelagic zone is a testament to the subtlety of nature. Every photon that penetrates the surface is a precious resource, and every flash of bioluminescence is a carefully crafted signal. The laws of optics shape the evolution of eyes, photophores, and camouflage. The study of this zone is not just a scientific endeavor. It is a journey into a world where light is rare and precious, where the darkness is neither empty nor silent, but filled with a constant faint glow. The mesopelagic zone is a physical laboratory, and each discovery reveals a new layer of complexity in the interaction between light and life. The physics of this zone continues to challenge our understanding, and the answers lie in the clear, cold water of the open ocean. Lanternfish swim in the dim blue light of the Twilight Zone, their bodies covered in tiny pinpoint lights. These fish belong to the family Myctophidae, and they represent approximately 65% of all deep-sea fish biomass. This staggering abundance means that lanternfish dominate the midwater layers of every ocean on Earth, forming a living blanket of life that stretches across the planet. Their photophores are arranged in species-specific patterns along their flanks, bellies, and heads, allowing scientists to identify different species even in the absolute darkness of the mesopelagic zone. Each species has a unique constellation of lights, a biological barcode that remains stable and distinct across generations. Lanternfish gather in enormous schools that can extend for miles, creating a dense carpet of bodies that blocks sonar pulses from surface ships. Early oceanographers mistook these schools for the actual seafloor, a phenomenon known as the false bottom. These schools move in coordinated, synchronized masses, their photophores flickering in rhythmic patterns that may serve as communication signals between individuals. The fish themselves are relatively small, typically ranging from 2 to 15 centimeters in length, with large eyes adapted to the faintest traces of light. Their bodies are covered in silvery scales that reflect the dim glow of their own photophores, making them appear as tiny, living stars in the endless dark. The lanternfish school is a self-contained ecosystem, with individuals constantly adjusting their positions to maintain cohesion. When a predator approaches, the school may flash its photophores in a sudden burst, confusing the attacker and allowing the fish to scatter. This collective defense mechanism is still not fully understood by scientists, who cannot explain how the fish coordinate such rapid, synchronized responses without a central command. The photophore patterns themselves are remarkably stable within each species, yet the evolutionary purpose of such intricate variation remains a subject of active research. Some species have photophores on their tongues, while others have them on their fins, suggesting that each species uses its lights in a unique way that has not yet been observed. Beneath the lanternfish, in the same layer of water, drifts a creature so numerous that it may hold the title of the most abundant vertebrate on Earth. The bristlemouth fish, belonging to the genus Cyclothone, are small, translucent fish that rarely exceed 8 centimeters in length. Their bodies are almost completely transparent, with only a faint outline of internal organs visible through the skin. This transparency helps them avoid detection by predators in the dim light of the Twilight Zone, where even a faint shadow can attract attention. Their name comes from the bristle-like teeth that line their jaws, which are hinged and can open wide to swallow prey larger than their own heads. Bristlemouths have a global distribution, with populations estimated in the trillions, making them far more numerous than any other fish species. Despite their abundance, they are rarely seen by humans because they live at depths between 200 and 1,000 meters, where sunlight never reaches. Their bodies are so fragile that they often disintegrate when brought to the surface in nets, leaving only fragments for scientists to study. The hinged jaw mechanism allows them to capture small crustaceans and other plankton with a quick snapping motion, and their stomachs can expand to accommodate large meals. The females are slightly larger than the males, and they produce bioluminescent light from specialized organs, though the purpose of this light is still debated among researchers. The bristlemouth's transparent body is not just a passive camouflage. It also contains reflective layers that help it blend with the surrounding water. When light from above penetrates the water, the fish's body reflects it in a way that minimizes its silhouette. This adaptation is so effective that even with sensitive cameras, scientists have difficulty spotting them in their natural habitat. The species Cyclothone microdon and Cyclothone eclinodons are the most common, but the exact number of species remains uncertain because of the difficulty in collecting intact specimens. Some researchers believe that bristlemouths may play a critical role in the ocean's carbon cycle, but this is outside the scope of our current focus. Rising slightly higher in the Twilight Zone, the Pacific hatchetfish of the genus Argyropelicus presents a different kind of mystery. These fish have a distinctive, flattened body that is compressed from side to side, giving them a hatchet-like shape. Their most remarkable feature is their tubular, upward-pointing eyes, which are fixed in position and cannot move. These eyes are designed to detect the faintest silhouette of prey or predators against the dim light filtering down from the surface. The eyes are so sensitive that they can perceive the faint glow of a single bioluminescent flash from hundreds of meters away. The silvery flanks of the hatchetfish are covered in a layer of reflective guanine crystals that act like a mirror. This mirror-like surface reflects the ambient light from above, canceling out the fish's own shadow and making it nearly invisible to predators looking up from below. The effect is so precise that the hatchetfish can adjust the angle of its body to maintain perfect camouflage as it moves through the water. The tubular eyes are oriented so that they point directly upward, giving the fish a narrow field of view but exceptional sensitivity to movement above. Scientists have studied the structure of these eyes under microscopes, but they still cannot fully explain how the hatchetfish processes such a limited visual field while navigating through a complex three-dimensional environment. The hatchetfish's body is also covered in photophores along its belly, which emit a faint blue-green light to match the downwelling light from the surface. This counter-illumination technique is a form of active camouflage, and it is one of the most sophisticated examples of bioluminescence in the ocean. The fish can adjust the intensity of its photophores to match the changing light levels as it moves through different depths. The exact mechanism by which the hatchetfish senses the ambient light and adjusts its own glow is still not fully understood, and it represents a subtle cliffhanger in the study of deep-sea vision. Some researchers suspect that the hatchetfish's pineal gland, which is located on the top of its head, plays a role in this light-sensing process, but the exact neural pathways remain a mystery. Descending deeper into the Twilight Zone, we encounter the dragonfish, a group of predators belonging to the family Stomiidae. These fish are named for their long, dragon-like barbels that hang from their chins like a fishing line. The barbel is tipped with a bioluminescent lure that pulses with a faint blue-green light, attracting small fish and crustaceans within striking range. The dragonfish itself is a slender, dark-bodied creature with large fang-like teeth that protrude from its mouth even when it is closed. These teeth are so long that the dragonfish must open its jaw wide to swallow prey, a process that can take several seconds. The most astonishing feature of the dragonfish is its ability to produce red light, a wavelength that is invisible to most other deep-sea creatures. The vast majority of mesopelagic animals have eyes that are sensitive only to blue light, which is the dominant wavelength at these depths. The dragonfish, however, has a second set of photophores near its eyes that emit a deep red glow. This red light acts like a covert searchlight, allowing the dragonfish to illuminate its prey without being detected. The prey cannot see the red light, so they have no warning of the predator's approach. The dragonfish's own eyes are equipped with a special pigment that is sensitive to red light, giving it an exclusive visual advantage in the dark. The red light of the dragonfish is produced by a complex chemical reaction involving a form of the protein luciferase that is unique to this family. Scientists have identified the gene responsible for this red light production, but the exact evolutionary pathway that led to this adaptation remains unclear. The barbel itself is highly flexible and can be retracted or extended at will, allowing the dragonfish to dangle the lure at different distances. Some species of dragonfish have barbels that are longer than their entire body, trailing behind them like a long, glowing thread. The function of these extra-long barbels is still being studied, and it is possible that they serve as a decoy to attract predators away from the dragonfish's head. In the same dark waters, drifting like a ghostly nebula, we find the siphonophore known as Praia dubia. This creature is not a single animal but a colony of individual zooids, each specialized to perform a specific function. Some zooids are responsible for feeding, others for reproduction, and still others for defense or locomotion. The colony is connected by a long, transparent stem that can reach lengths of 40 to 50 meters, making Praia dubia one of the longest animals on Earth. The entire colony drifts through the water, using a jet propulsion system created by the coordinated pulsing of its swimming bells. The colony's feeding zooids are equipped with stinging cells that can paralyze small fish and crustaceans. Once prey is captured, it is passed along the stem to the digestive zooids, which break it down into nutrients that are shared throughout the colony. The defense zooids produce a bright bioluminescent flash that can startle predators, giving the colony time to retract its stem and escape. The entire arrangement is so efficient that the colony can survive for months in the nutrient-poor waters of the Twilight Zone. Despite its enormous length, the colony is incredibly fragile, and it is rarely seen intact because the netting process often tears it apart. The siphonophore's colony structure is a mystery to scientists because the individual zooids are genetically identical, yet they differentiate into specialized forms during development. The trigger for this differentiation is not fully understood, and it represents one of the great puzzles of developmental biology. The colony operates as a single unit, with a shared nervous system that coordinates the pulsing of the swimming bells and the retraction of the feeding tentacles. The stem itself is transparent and gelatinous, making it nearly invisible in the water. This transparency extends to the entire colony, allowing it to drift through the water without being seen by predators or prey. Finally, we encounter the vampire squid, a creature whose scientific name, Vampiroteuthis infernalis, means vampire squid from hell. Despite its fearsome name, the vampire squid is not a true squid. It belongs to its own order, Vampiromorphida, and it is a living fossil that has remained unchanged for millions of years. Its body is covered in a dark, velvety skin that is interrupted by a series of photophores, which it can flash to confuse predators. The most striking feature of the vampire squid is its webbing, which connects its 8 arms like a cloak. When threatened, the vampire squid turns its arms inside out, wrapping them over its body to form a spiky protective ball. The vampire squid does not hunt prey like other cephalopods. Instead, it feeds on marine snow, the constant drift of organic debris that sinks from the surface layers. It extends a long, filamentous structure called a scarce from each arm, which is covered in sticky hairs that trap particles of food. The vampire squid then uses its mouth to scrape the particles off the cirri and ingest them. This feeding method is unique among cephalopods, and it allows the vampire squid to survive in the low-energy environment of the Twilight Zone. The webbing also helps the vampire squid capture food by creating a net that funnels the marine snow toward its mouth. The vampire squid's eyes are the largest relative to body size of any animal on Earth, measuring up to 2.5 centimeters in diameter, in a creature that is only about 30 centimeters long. These enormous eyes are adapted to the faint light of the mesopelagic zone, where the vampire squid lives at depths between 600 and 900 meters. The eyes can detect the faintest bioluminescent flashes, which may come from approaching predators or potential mates. The vampire squid also has a pair of organ-like structures called photophores that are located on the tips of its arms, which it can use to produce a faint blue glow. The exact purpose of these arm-tip photophores is still debated, but they may serve as a distraction to attract predators away from the squid's body. The hatchetfish is one of the most perfectly adapted creatures in the Twilight Zone, with a body that resembles a silver axe blade. Its thin, compressed shape allows it to move through the water with minimal resistance, while its large, upward-pointing eyes scan the dim light above for the silhouettes of prey. The hatchetfish's belly is lined with photophores that produce a faint, downward-directed light, a technique called counter-illumination that cancels out its own shadow. This makes the fish virtually invisible to predators lurking below, who would otherwise see a dark shape against the faint surface light. The hatchetfish can adjust the intensity of its bioluminescence to match the changing light levels as it migrates vertically through the water column each night. The lanternfish, or myctophid, is the most abundant fish in the mesopelagic zone, with an estimated global population in the hundreds of billions. These small fish, typically measuring between 2 and 15 centimeters in length, possess photophores arranged in species-specific patterns along their flanks and bellies. The patterns are so distinct that scientists can identify different lanternfish species simply by the arrangement of their lights. Lanternfish also have a reflective layer behind their retinas called the tapetum lucidum, which amplifies any available light and gives them exceptional night vision. This adaptation is crucial for their daily vertical migrations, which can cover hundreds of meters as they ascend to feed on plankton near the surface at night. The siphonophore is a colonial organism that challenges the very definition of an individual animal. It is composed of many specialized units called zooids, each of which performs a specific function such as feeding, reproduction, or movement. These zooids are genetically identical and physically connected, forming a single entity that can stretch over 40 meters in length, making it one of the longest animals on Earth. The feeding zooids are equipped with stinging cells called nematocysts, which can paralyze small fish and crustaceans. The siphonophore's bioluminescence is often a brilliant blue or green, and it can produce flashing patterns that may serve to attract prey or confuse predators. The deep-sea jellyfish, or medusa of the Twilight Zone, have evolved a range of strategies to survive in a world of scarce food and constant pressure. Many species have a bell that is extremely thin and transparent, allowing them to ambush prey with minimal detection. The Atolla jellyfish, also known as the alarm jellyfish, produces a spectacular display of bioluminescence when attacked, creating a swirling pinwheel of light that is thought to attract even larger predators to the attacker. This is a form of defense known as the burglar alarm hypothesis, where the jellyfish sacrifices itself to draw attention to its predator, giving the jellyfish a chance to escape in the confusion. The Atolla's bell is only about 5 centimeters in diameter, but its tentacles can extend for several meters, trailing behind it like a living net. The bristlemouth fish, genus Cyclothone, is arguably the most abundant vertebrate on Earth, with trillions of individuals inhabiting the mesopelagic zone worldwide. These fish are tiny, typically less than 8 centimeters in length, and they possess a mouth filled with needle-like teeth that are disproportionately large for their size. The bristlemouth's body is covered in photophores, and it can produce a faint glow that may help it communicate with others of its species in the darkness. Despite their abundance, bristlemouths are rarely encountered by humans because they spend their entire lives in the deep ocean, only migrating short distances vertically. Their role in the carbon cycle is significant, as they consume vast quantities of zooplankton and later excrete carbon-rich fecal pellets that sink to the deep sea. The cock-eyed squid Histiotuthis is a remarkable example of asymmetrical adaptation in the Twilight Zone. Its left eye is much larger than its right eye, sometimes reaching twice the diameter, and it is oriented upward to detect the faint silhouettes of prey against the surface light. The right eye is smaller and looks downward, scanning for bioluminescent flashes from potential predators or prey below. This dual eye system allows the squid to monitor two different visual environments simultaneously, a strategy that is unique among cephalopods. The cockeyed squid also has a complex system of chromatophores, allowing it to change its skin color and texture for camouflage. Its body is covered in photophores that can produce a dim blue-green light, which may be used to match the downwelling light from above, a form of counter-illumination similar to that of the hatchetfish. The pelagic octopus, Japatella, is a small, gelatinous creature that lives in the mesopelagic zone and has evolved a remarkable method of escape. When threatened, it can rapidly change its body color from transparent to a deep dark red, making it nearly invisible to predators that use bioluminescent searchlights. The red pigment absorbs blue light, which is the dominant wavelength in the Twilight Zone, so the octopus effectively disappears. Japatella also has the ability to produce bioluminescent flashes from its skin, though the purpose of this is not fully understood. Its body is soft and fragile, with a gelatinous consistency that allows it to withstand the high pressure of its environment. This octopus feeds primarily on small crustaceans and other gelatinous organisms, using its arms to capture them in the dark. The deep-sea shrimp, such as those in the family Oplophoridae, are among the most bioluminescent creatures in the Twilight Zone. They produce a luminous cloud from glands located near their mouthparts, which can confuse and blind predators long enough for the shrimp to escape. Some species also have photophores on their legs and antennae, creating a moving light show that can disorient attackers. The shrimp's exoskeleton is often transparent or lightly pigmented, allowing it to blend into the dim water column. Their compound eyes are highly sensitive to the faintest light, and they can detect the bioluminescent signals of other creatures from considerable distances. These shrimp are a crucial part of the mesopelagic food web, serving as prey for fish, squid, and larger invertebrates. The dragonfish genus Stomidae is a formidable predator of the Twilight Zone, with a body that can reach up to 40 centimeters in length. Its most distinctive feature is a long chin-like barbel that is tipped with a bioluminescent lure, which it dangles in front of its mouth to attract prey. The dragonfish's teeth are long and sharp, and they are so large that they protrude from its mouth even when it is closed, giving it a fearsome appearance. Some dragonfish species produce red bioluminescence, which is unusual because most deep-sea creatures can only see blue light. This adaptation allows the dragonfish to illuminate its prey without being seen itself, as the red light is invisible to other animals. The dragonfish's eyes are also adapted to detect red light, giving it a unique advantage in the darkness. The catignath, or arrowworm, is a small, transparent predator that is among the most abundant planktonic animals in the mesopelagic zone. Its body is streamlined and equipped with rows of spines near its head, which it uses to grasp and immobilize its prey. The arrowworm can swim in short, rapid bursts to ambush small crustaceans and fish larvae. Some species are bioluminescent, producing a blue-green glow that may serve as a warning to predators or as a lure to attract mates. The catignath's nervous system is remarkably simple, yet it is capable of coordinating complex hunting behaviors. These creatures are so numerous that they play a significant role in the transfer of energy from lower to higher trophic levels in the Twilight Zone. The deep-sea ctenophore, or comb jelly, is a gelatinous predator that uses rows of tiny, hair-like cilia to propel itself through the water. These cilia refract light, creating a shimmering rainbow-like effect that is often mistaken for bioluminescence. Ctenophores are among the most delicate creatures in the ocean, with bodies that are composed almost entirely of water and can be damaged by the slightest touch. They feed on small plankton by extending their sticky tentacles, which are lined with colloblasts that trap prey upon contact. Some ctenophores in the mesopelagic zone are bioluminescent, producing a bright blue light when disturbed. This light may startle predators or attract larger predators to the attacker, similar to the burglar alarm strategy of the Atolla jellyfish. The giant ostracod, Gigantocyprus, is a crustacean that resembles a tiny translucent clam with a pair of large bulbous eyes. Its body is enclosed in a bivalve-like carapace, and it can reach up to 3 centimeters in diameter, making it one of the largest ostracods in the ocean. The giant ostracod's eyes are so large that they take up most of its head, and they are adapted to detect the faintest bioluminescent flashes. It is a slow-moving predator that feeds on small copepods and other zooplankton, using its antennae to sense vibrations in the water. The giant ostracod is also known for producing a bright, greenish bioluminescence from glands on its body, which may be used for mating displays or to confuse predators. Its carapace is so transparent that its internal organs are visible, giving it an almost ghostly appearance in the dim light of the Twilight Zone. The deep-sea anglerfish, which is more commonly associated with the bathypelagic zone, also has species that inhabit the upper reaches of the mesopelagic zone. These fish have a distinctive bioluminescent lure that protrudes from the top of their head, which they use to attract prey in the darkness. The lure is actually a modified dorsal fin ray, and it is filled with symbiotic bacteria that produce light. The anglerfish's mouth is large and lined with sharp, inward-pointing teeth, ensuring that any prey that is lured in cannot escape. In many species, the male is much smaller than the female and attaches himself permanently to her body, fusing his tissues with hers and becoming a parasitic sperm donor. This adaptation ensures that the male can find a mate in the vast emptiness of the deep sea, where encounters are rare. The marine snow that falls through the mesopelagic zone is not just a passive rain of particles, it is also a living ecosystem in itself. Tiny particles of organic matter are colonized by bacteria, which break them down and release nutrients. These particles are also consumed by small zooplankton such as copepods and appendicularians, which in turn are preyed upon by larger creatures. The marine snow forms a critical link between the productive surface waters and the deep ocean, transporting carbon and energy downward. Some of these particles are so small that they can remain suspended in the water column for months, while others are large enough to be seen with the naked eye, resembling fluffy, white flakes falling through the darkness. The mesopelagic zone is thus a realm of constant recycling, where nothing is wasted and every particle is a source of life. Among the most abundant inhabitants of the mesopelagic zone are the lanternfish, belonging to the family Mectophytae. These small fish, typically ranging from 2 to 30 centimeters in length, possess photophores along their bellies and flanks that produce a faint blue-green light. The pattern of these light organs is species-specific, allowing individuals to recognize their own kind in the near-total darkness. Lanternfish are believed to be the most numerous fish in the world, with estimates suggesting that their biomass may exceed that of all other fish combined. They form a critical trophic link, consuming zooplankton and being preyed upon by larger fish, squid, and marine mammals. The hatchetfish of the family Sternoptichidae are another striking example of mesopelagic adaptation. Their bodies are extremely compressed laterally, resembling a silver hatchet blade, with upward-facing eyes that scan for silhouettes of prey against the faint light from above. Hatchetfish possess photophores on their ventral surfaces that emit light at a specific intensity and wavelength, matching the downwelling light from the surface. This counter-illumination effectively erases their silhouette, making them nearly invisible to predators lurking below. Some species can adjust the brightness of their bioluminescence in real time to match changing light conditions as they migrate vertically. Many dragonfish, belonging to the family Stomiidae, are ambush predators with elongated bodies and enormous jaws filled with needle-like teeth. Their most remarkable adaptation is the ability to produce red light, a rare feature in the deep sea because most organisms cannot see red wavelengths. Dragonfish use a specialized suborbital photophore that emits a far red glow, invisible to most prey, allowing them to illuminate their surroundings without being detected. They also possess a long barbel, a chin appendage tipped with a luminous lure, which they use to attract small fish and crustaceans. The red light may also serve as a private communication channel between dragonfish, hidden from the eyes of other predators. The diel vertical migration, or DVM, is one of the most massive animal movements on Earth. Each night, billions of mesopelagic organisms ascend from depths of several hundred meters to the surface waters to feed on plankton, then descend again before dawn. This migration is driven by the trade-off between feeding in productive surface waters and avoiding visual predators. The speed of ascent can reach several meters per minute, and the total distance traveled can be hundreds of meters. Many species exhibit a reverse migration pattern, where they remain deep during the day and ascend at night, but some migrate only partially, staying in the lower mesopelagic. The sensory systems of mesopelagic creatures are exquisitely tuned to their dim environment. Many fish have large tubular eyes that maximize light capture, with retinas dominated by rod cells sensitive to the blue-green wavelengths that penetrate deepest. The giant eyes of the barrel-eye fish, Macropina microstoma, are contained within a transparent, fluid-filled dome on top of its head. These eyes can rotate to look upward through the dome or forward, allowing the fish to spot prey or predators in multiple directions. The lateral line system, which detects vibrations and pressure changes, is highly developed in many mesopelagic species, enabling them to sense the movements of nearby animals in the dark. Reproduction in the mesopelagic zone is often a matter of chance and efficiency. Besides the extreme sexual parasitism seen in anglerfish, many species produce large numbers of tiny eggs that are released into the water column. These eggs develop into larvae that feed on plankton and eventually metamorphose into adults. Some fish, like the bristlemouths in the genus Cyclothone, are simultaneous hermaphrodites, possessing both male and female reproductive organs, which increases the likelihood of successful fertilization when populations are sparse. The gonads of many mesopelagic fish are proportionally large, reflecting the need to produce many offspring in a low-density environment. Feeding strategies in the mesopelagic zone are diverse and specialized. Many zooplankton, such as copepods and krill, are filter feeders that strain tiny particles from the water using fine setae. Others, like the catagnaths or arrow worms, are ambush predators that dart forward to capture small prey with grasping spines. The pelagic squid, such as those in the family Cranchidae, have transparent bodies filled with ammonium chloride solution, which provides neutral buoyancy and allows them to hover motionlessly in the water column. Their large eyes and rapid tentacle strikes make them effective predators of fish and crustaceans. Gelatinous organisms are abundant in the mesopelagic zone, and their fragile bodies are often overlooked by deep-sea sampling methods. Jellyfish, comb, jellies, and siphonophores drift through the water, capturing prey with stinging cells or sticky tentacles. The deep-sea medusa, such as the species in the genus Paraphila, can reach large sizes and possesses a bioluminescent display when disturbed. Siphonophores, which are colonial organisms composed of specialized zooids, can extend their tentacles over many meters to ensnare small fish and crustaceans. The sheer biomass of gelatinous zooplankton in the mesopelagic may rival that of fish, yet their ecological role is still poorly understood. Crustaceans are another dominant group in the mesopelagic fauna. Shrimp-like amphipods, such as those in the family Hyperidae, are often associated with gelatinous zooplankton, either as parasites or as hitchhikers. The deep-sea shrimp of the genus Acanthophera have large reflective eyes and are capable of rapid swimming to escape predators. Some species of copepods, such as the genus Pareucata, are themselves predators of other small crustaceans, using their sharp mandibles to capture and consume prey. The vertical distribution of these crustaceans is closely tied to the availability of marine snow and the DL migration of their prey. The extreme pressures of the mesopelagic zone, ranging from about 10 to 100 atmospheres, have driven profound physiological adaptations. Many fish lack swim bladders, or have swim bladders filled with wax esters instead of gas, to avoid the buoyancy problems of compression. Their muscles are often watery and less dense, and their skeletons are reduced in calcium to minimize energy expenditure. The metabolic rates of mesopelagic fish are generally low, allowing them to survive on the sporadic food supply that falls from above. Some species can drastically reduce their metabolism when food is scarce, entering a state of torpor that conserves energy. The deep scattering layer, a phenomenon detected by sonar, is caused by the aggregation of these mesopelagic organisms. This layer rises and falls with the DL migration, and its composition varies with depth and time of day. The layer is not a single uniform sheet, but a patchwork of different species and age classes, each responding to local conditions. The scattering layer can be so dense that it obscures the seafloor from sonar, and it has been a major obstacle for naval operations. Scientists are still mapping the distribution and abundance of these organisms using advanced acoustic and optical technologies. Despite decades of research, many mesopelagic species remain unidentified or poorly described. The deep sea is vast, and sampling efforts are limited by cost and technology. New species are discovered regularly, often from specimens collected by remotely operated vehicles or submersibles. The taxonomic challenges are compounded by the fact that many species are fragile and easily damaged during collection. The role of the mesopelagic zone in global biogeochemical cycles, particularly in carbon sequestration, is an active area of study. The marine snow that falls through this zone, along with the daily migration of organisms, transports significant amounts of carbon from the surface to the deep ocean, a process that influences Earth's climate. The mesopelagic zone is not a lifeless void, but a dynamic, interconnected ecosystem. Each creature, from the tiniest copepod to the largest squid, plays a role in the cycling of matter and energy. The adaptations that allow them to survive in this challenging environment are a testament to the power of evolution. Yet, much remains unknown. The Twilight Zone is one of the least explored habitats on Earth, and the creatures that live there hold secrets that scientists are only beginning to understand. As technology advances, we will likely uncover more of these mysteries, but for now, the mesopelagic fauna remains a realm of wonder and scientific inquiry. Under the darkening veil of dusk, the ocean stirs with a movement so vast and so precisely timed that it remains one of the most extraordinary phenomena on Earth. This is the Deal Vertical Migration, or DVM, and it is the largest daily animal migration on the planet by both biomass and number of individuals. Billions upon billions of organisms, from tiny crustaceans to small fish and squid, ascend from the deep Twilight Zone toward the surface waters every evening, only to retreat back into the abyss before the first light of dawn. The migration is a synchronized, nightly pilgrimage that begins as the sun dips below the horizon. When the last rays of daylight fade, a signal passes through the water column, triggering a mass upward movement that can involve more than 10 billion metric tons of living creatures. These organisms rise from depths of 200 to 1,000 meters, where they spend the day hidden in near darkness, and they climb toward the sunlit surface layers, sometimes reaching within a few meters of the air-sea interface. By dawn, they have reversed course, descending again to their daytime refuge, and the cycle repeats every single day, year after year, without fail. The participants in this migration are as diverse as they are numerous. Lanternfish of the family Myctophidae are among the most abundant vertebrates on Earth, and they form a core component of the migrating biomass. These small, silvery fish possess light-producing organs along their bellies, but it is their daily vertical journey that defines their role in the ocean. Euphausid krill, the shrimp-like crustaceans that swarm in vast numbers, also join the nightly ascent, propelling themselves upward with rapid strokes of their swimming legs. Copepods, the tiny crustaceans that dominate the zooplankton, migrate as well, though they are so small that their movements are often measured in centimeters per minute rather than meters per second. Squid and jellyfish add a softer, more gelatinous presence to the migration. Many species of squid, such as the Boro-Pacific armhook squid, rise from the depths to feed on the same prey that the fish and krill are pursuing. Gelatinous zooplankton, including comb jellies and various medusae, also participate, though their slow, pulsing movements make them less conspicuous than the fast-swimming lanternfish. Together, these organisms create a living river that flows upward through the water column every night. A river that is invisible to the human eye, but detectable by other means. The depth of the migration varies depending on the species, the location, and the season. Most organisms that live in the Twilight Zone, which spans roughly 200 to 1,000 meters below the surface, will ascend to the epipelagic zone, the sunlit top 200 meters of the ocean. Some species, particularly the larger lanternfish and squid, may travel from depths of 800 meters or more all the way up to 50 meters or even shallower. The speed of their ascent is remarkable. Typical migration rates range from 1 to 10 centimeters per second, but some fish and krill can achieve bursts of up to 20 centimeters per second. At these speeds, a journey of 400 meters can take just over an hour, meaning that the migration is often completed within the narrow window of twilight. The reason for this daily commute is rooted in a fundamental trade-off between safety and sustenance. During the day, the surface waters are bathed in sunlight, which makes them a dangerous place for small plankton-feeding animals. Visual predators such as tuna, mackerel, seabirds, and even larger fish can easily spot and capture prey in the bright, well-lit layers. By hiding in the dark depths of the Twilight Zone during daylight hours, these organisms avoid being eaten. But the depths are also a food desert. The phytoplankton that forms the base of the ocean food web can only grow in the sunlit surface waters, where photosynthesis occurs. So at night, under the cover of darkness, the migrants ascend to the surface to feed on the rich bloom of phytoplankton and small zooplankton that have spent the day growing and reproducing in the light. The migration is not a simple, uniform movement. It is a complex, layered phenomenon, with different species ascending to different depths and at different times. Some organisms, particularly the copepods, may only rise a few hundred meters, while others, like certain lanternfish, may travel the full distance from the lower Twilight Zone to the surface. The timing is also influenced by the moon. On bright, moonlit nights, some species remain deeper to avoid the increased visibility, while on dark, moonless nights, they may ascend to shallower waters. This sensitivity to light is the primary trigger for the migration, and it is why the movement is so closely tied to the diel cycle of day and night. The discovery of the diel vertical migration in its full global scale came not from biologists studying the ocean, but from naval sonar operators during World War II. In the early 1940s, as submarines and surface ships began using active sonar to detect enemy vessels, a strange phenomenon appeared on their screens. A strong, continuous echo would appear at a depth of around 300 to 500 meters, and it would rise toward the surface at dusk and then sink back down at dawn. At first, the operators were baffled. Some thought the seafloor itself was moving, or that there was a phantom layer of the ocean that was somehow shifting. But further investigation revealed that the echo was not from the bottom or from any solid object. It was from millions of tiny organisms, each with a gas-filled swim bladder or a similar acoustic reflector, that were collectively creating a false seafloor. This echo became known as the Deep Scattering Layer, or DSL, and it is one of the most persistent features of the ocean's acoustic landscape. The DSL is so dense with reflecting organisms that it can absorb or scatter sound waves, making it difficult for sonar to penetrate deeper. During the war, this layer was a practical nuisance, but it also became a scientific gold mine. After the war, researchers began to study the DSL in detail, using echo sounders to map its depth, thickness, and daily movements. They soon realized that the layer was not a single static entity, but a dynamic, shifting aggregation of life that rose and fell with the sun. The discovery of the DSL confirmed the existence of the diel vertical migration on a planetary scale, and it showed that the Twilight Zone was not a barren, empty space, but a zone of constant, large-scale movement. The energetics of the DL vertical migration are a puzzle that scientists have been trying to solve for decades. Moving a body of water upward against gravity requires a significant expenditure of energy, and for a small organism, swimming hundreds of meters each day is a costly endeavor. The metabolic cost of the ascent and descent can be high, often amounting to a substantial fraction of the organism's daily energy budget. For example, studies on lanternfish have shown that the energy required to swim up and down can account for 20 to 30% of their total daily energy consumption. Krill, which are weaker swimmers, face an even greater challenge, and they must carefully balance the energy they gain from feeding against the energy they burn during the migration. Yet the feeding gain is usually sufficient to justify the cost. The surface waters at night are rich in phytoplankton and small zooplankton, and the migrants can feed intensively during the few hours they spend there. The carbon and nutrients they acquire are then used for growth, reproduction, and maintenance. But the migration also creates a net loss of energy from the system, because the organisms that ascend to feed must return to the depths, and they carry with them the carbon they have consumed. This is where the DL vertical migration becomes a key player in the ocean's carbon cycle. The process is known as the biological pump, and the DVM is a major component of it. When the migrants feed in the surface waters at night, they ingest carbon-rich organic matter, including phytoplankton and other tiny particles. Some of this carbon is immediately used for respiration, and the carbon dioxide is released back into the water. But a significant portion is stored in the organism's bodies as fat, proteins, and other tissues. When the migrants descend back to the Twilight Zone at dawn, they transport this carbon with them, effectively moving it from the surface to the deep ocean. There, the carbon can be released in several ways: through respiration at depth, through the excretion of waste products, or through the death and decomposition of the organisms themselves. The carbon that is transported to the deep ocean by the DVM is removed from the atmosphere for long periods. Once it sinks below the mixed layer, typically below 200 meters, it is no longer in contact with the air, and it can be sequestered for centuries or even millennia. Some estimates suggest that the Deal vertical migration accounts for the transport of as much as 1.5 billion metric tons of carbon per year, a significant fraction of the total carbon that is exported from the surface to the deep sea. This carbon pump is a crucial part of the Earth's climate system, helping to regulate atmospheric carbon dioxide levels and, by extension, global temperatures. But the full picture of the DVM's role in the carbon cycle is still incomplete. Scientists have measured the migration in many parts of the ocean, but they have not yet accounted for all the variability. The depth of the migration, the number of participants, and the amount of carbon they carry can change with seasons, ocean currents, and even the availability of food. Furthermore, the organisms themselves are not just passive transporters of carbon. They are also active consumers, and their feeding and excretion can alter the chemistry of the water at different depths. The DVM is a dynamic, interconnected system, and every piece of the puzzle reveals new questions. As the night deepens and the migrants reach their feeding grounds, the ocean surface becomes a churning, living soup. Lanternfish, krill, and copepods swarm in dense aggregations, their movements creating faint bioluminescent trails that are visible only to the most sensitive instruments. The squid and jellyfish follow, their translucent bodies drifting through the darkness. The entire scene is a blur of motion, a feeding frenzy that is both violent and silent. And then, as the first hints of gray appear in the eastern sky, the migration begins to reverse. The organisms start their descent, sinking back into the depths, and by the time the sun rises, the surface waters are once again empty. But here is a cliffhanger that scientists still cannot explain. Recent studies using advanced acoustic sensors have revealed that some individuals, particularly among the lanternfish, do not always complete the full daily migration. Instead, they perform what is called a partial migration, stopping at intermediate depths or remaining in the surface waters for longer than expected. No one knows why these individuals break the pattern. Some theories suggest it could be related to individual variation in energy reserves, or to social cues within the school, or to some unknown environmental factor that has not yet been measured. The fact that the migration is not as uniform as once thought raises deeper questions about the control and coordination of this massive movement. If the largest migration on Earth has exceptions that cannot be predicted, then what other secrets does the Twilight Zone still hold? The mechanics of this daily descent are governed by a precise interplay of physiology and physics. Most Twilight Zone organisms rely on gas-filled swim bladders to maintain neutral buoyancy at their preferred depth. But adjusting these bladders for a 500-meter vertical commute requires significant energy. Lanternfish, for example, must actively secrete gas into their swim bladders during ascent and reabsorb it during descent, a process that can take hours and is limited by the rate of gas exchange across the swim bladder wall. This physiological constraint means that the upward migration cannot be instantaneous. It proceeds at a steady pace of roughly 1 to 2 meters per minute, dictated by the fish's ability to adjust its buoyancy without rupturing its swim bladder from rapid pressure changes. The trigger for the migration is not a single cue, but a cascade of sensory inputs that begin deep in the water column. As sunlight fades, the angle of polarized light decreases, and the rate of change in light intensity is detected by specialized photoreceptors in the eyes of krill, lanternfish, and other migrators. These organisms possess visual pigments that are exquisitely sensitive to the blue-green wavelengths that penetrate deepest, allowing them to perceive the twilight even at depths where human eyes would see only black. Experiments have shown that if the light level is held constant artificially, the migration does not occur, proving that the rate of change, not the absolute brightness, is the critical signal. Once the descent begins, the organisms must navigate a series of thermal barriers that can slow or stop their progress. The thermocline, a layer of rapid temperature change between the warm surface and cold, deep water, acts as a density gradient that requires additional energy to cross. For small crustaceans like copepods, which are only a few millimeters long, the viscosity of water changes with temperature, making their swimming strokes less efficient in colder water. To compensate, they increase their swimming speed or adjust their body orientation, but this comes at a metabolic cost that can deplete their energy reserves over the course of a single migration. The speed and direction of the descent are also influenced by internal biological clocks that are synchronized with the day-night cycle. These circadian rhythms are not simply passive responses to light. They are driven by a molecular clock in the brain that continues to tick even in constant darkness. In laboratory studies, zooplankton and fish kept in total darkness still show a rhythmic pattern of vertical movement for several days, though the timing gradually drifts. This suggests that the migration is not purely a reaction to sunlight, but a programmed behavior that is fine-tuned by environmental cues. During the descent, the organisms must also contend with the risk of predation from below. Certain deep-sea predators, such as the six-gill shark and the giant squid, are known to patrol the upper Twilight Zone during the day, waiting for stragglers that descend too slowly or become disoriented. To avoid detection, many migrators use bioluminescent counter-illumination, matching the dim light from above on their ventral surfaces to erase their silhouette against the fading daylight. This is an active process requiring energy to produce light, and it must be precisely calibrated to the changing light levels at each depth. The descent is not a continuous free fall, but a series of pauses and adjustments that allow the animals to sample their environment. Recent acoustic tracking of individual lanternfish has revealed that they often stop at intermediate depths for several minutes, perhaps to feed on vertically migrating plankton that are also moving downward or to avoid patches of predators. These pauses are not random. They occur at specific depths where temperature or oxygen levels change, suggesting that the animals are making decisions based on sensory input from their lateral line and chemoreceptors. The role of the Earth's magnetic field in guiding the migration is a growing area of research. Some species of copepods and krill have been shown to possess magnetite crystals in their tissues, which could allow them to sense the inclination and intensity of the magnetic field as they move through the water column. This would provide a backup navigational system when light levels are too low for visual cues, particularly during the descent into the pitch-black depths of the Twilight Zone. However, the exact mechanism of magnetic sensing remains unconfirmed, and scientists are still debating whether it plays a significant role in the daily migration. The energy efficiency of the migration is a delicate balance between the costs of ascending and descending and the benefits of feeding in the surface waters. For a lanternfish weighing 10 grams, the round trip of 500 meters requires an estimated 10 to 20% of its daily energy budget, a substantial investment that must be repaid by the food it consumes. Young fish, which have smaller energy reserves, often migrate to shallower depths than adults, reducing the distance they travel. This ontogenetic shift in migration behavior is another layer of complexity that scientists are only beginning to quantify. The physical effort of swimming against the water column's currents is another factor that shapes the migration mechanics. The Twilight Zone is not a static environment. It is crisscrossed by internal waves, upwellings, and eddies that can carry organisms sideways or even upward against their intended direction. To maintain a consistent vertical trajectory, migrators must constantly adjust their swimming angle and speed, using their lateral line to sense the water's motion and their swim bladder to compensate for changes in buoyancy from salinity variations. This adds a layer of dynamic control that is still not fully understood. The descent is also influenced by the availability of oxygen in the water column. In many parts of the ocean, there is an oxygen minimum zone between 100 and 1,000 meters, where oxygen levels drop to less than 0.5 milliliters per liter. Organisms that migrate through this zone must either tolerate low oxygen for short periods or have adaptations like hemoglobin with high oxygen affinity. Some lanternfish species have been found to increase their gill surface area or reduce their metabolic rate during the descent to conserve oxygen, while others simply avoid the oxygen minimum zone by altering their migration depth. This variation in physiological tolerance creates a mosaic of migration patterns across the global ocean. The role of sound in the migration is a fascinating and underexplored aspect. The deep, scattering layer, which is the acoustic signature of the migrating biomass, is not just a passive echo. The organisms themselves produce sounds as they move. Krill, for instance, generate clicks and snaps with their feeding appendages, and lanternfish emit low-frequency grunts from their swim bladder muscles. These sounds could serve as a form of communication or echolocation within the migrating school, helping individuals maintain cohesion in the dark. But the exact function of these acoustic signals remains unknown, and scientists are only now deploying hydrophone arrays to listen to the Twilight Zone's daily symphony. The descent is not a solitary journey. It is a coordinated movement of billions of individuals that must maintain spacing to avoid collisions and to maximize feeding efficiency. Schools of lanternfish use visual cues and lateral line sensing to keep a distance of about 1 to 2 body lengths from each other, a spacing that is maintained even in the dark by the faint bioluminescent glow of the fish themselves. This social organization ensures that the group moves as a cohesive unit, but it also imposes a constraint on the descent speed. If one fish slows down, the entire school adjusts its pace to maintain formation. The role of turbulence in the migration is another factor that scientists are beginning to explore. Turbulent eddies generated by the mixing of surface and deep water can create patches of higher or lower density that affect the buoyancy of small organisms. For copepods and krill, which are only a few centimeters long, a turbulent patch can cause them to be swept away from their intended course, requiring additional effort to return to the migrating group. Some studies suggest that these organisms can sense turbulence through their antennae and adjust their swimming strokes to minimize drift, but the neural mechanisms for this are still poorly understood. The descent ends when the organisms reach their daytime depth, which is not a fixed point but a range that varies with species, age, and environmental conditions. For most lanternfish, this depth is between 200 and 400 meters, where the water is cold and dark enough to provide concealment from surface predators. But the exact depth is chosen based on a combination of light levels, temperature, and the presence of prey. Once they arrive, the fish and krill reduce their metabolic rate to conserve energy, entering a state of torpor that lasts until the next evening's ascent. This resting phase is critical for their survival, allowing them to recover from the exertion of the migration. The energy cost of the descent is not uniform across the migration. The first 100 meters are the most energetically demanding because the pressure change is greatest and the swim bladder adjustment is most rapid. As the organisms descend deeper, the pressure changes become more gradual and the swim bladder volume decreases, reducing the buoyancy force that must be overcome. This means that the descent is like a controlled fall with a decreasing energy requirement, but the initial push is the hardest part. Scientists have calculated that the descent phase accounts for about 60% of the total energy expenditure of the migration, with the ascent phase requiring the remaining 40%. The apparent simplicity of the diel vertical migration masks a system of staggering complexity where each individual organism must integrate multiple sensory inputs, physiological constraints, and behavioral rules to complete its daily journey. The exceptions that scientists have observed, such as partial migration, are not anomalies but windows into this complexity. They reveal that the migration is not a fixed program, but a flexible behavior that can be adjusted in response to internal state and external conditions. Understanding these adjustments requires a deeper knowledge of the neural and hormonal control of migration, a field that is still in its infancy. The mechanics of the migration also involve a remarkable synchronization between the organisms and the Earth's rotation. The timing of the descent is not simply a reaction to the setting sun, it is anticipated by the internal clock, which begins to prepare the body for the journey hours before the actual start. This preparation includes changes in heart rate, blood flow, and hormone levels, all of which are orchestrated by the circadian system. The result is a highly coordinated movement that begins at the same time each day, within a few minutes of sunset, regardless of cloud cover or water clarity. The descent is also a time of intense sensory processing, as the organisms must constantly monitor their surroundings for predators, prey, and conspecifics. The lateral line, which detects water movements and pressure changes, is especially important in the dark, where vision is limited. It allows the fish to feel the approach of a predator or the presence of a schoolmate within a radius of several meters. This sense is so acute that some lanternfish can detect the wake of a swimming squid from over 20 meters away, giving them time to adjust their depth or speed to avoid detection. The role of the swim bladder in the descent is not limited to buoyancy control. It also serves as a resonating chamber for sound production and detection. The swim bladder is connected to the inner ear by a series of bones called the Weberian apparatus, which amplifies sound vibrations. This allows the fish to hear the low-frequency sounds of the ocean, such as the rumbling of waves or the calls of whales, which may provide additional cues for navigation. The swim bladder's volume changes with depth, altering the resonant frequency of the sound it can detect. and the fish must constantly adjust this sensitivity as it descends. The descent of the diel vertical migration is a testament to the adaptability of Twilight Zone organisms, which have evolved to exploit a narrow window of opportunity in the surface waters each night. The mechanics of this journey are still being unraveled, with each new study revealing more layers of complexity. The partial migration observed in some lanternfish is just one example of the variability that challenges our understanding. As scientists deploy more sophisticated instruments, such as deep-sea gliders and autonomous underwater vehicles, they are beginning to see that the migration is not a monolithic event, but a mosaic of individual decisions, each shaped by the unique physiology and experience of the organism. This revelation transforms the Twilight Zone from a simple layer of migrating animals into a dynamic, living system that is still full of unanswered questions. The descent begins with a physiological shift that is both subtle and profound. As the lanternfish leaves the surface waters, it must rapidly adjust its swim bladder to compensate for the increasing pressure, a process that consumes energy and requires precise neural control. The swim bladder is not merely a hydrostatic organ. It is intricately linked to the fish's ability to detect sound, and as the fish sinks, the volume of gas within the bladder compresses, altering the resonant frequency and thus the range of sound frequencies it can perceive. This change in hearing sensitivity is not a passive consequence, but an active adaptation, allowing the fish to tune into the different acoustic landscape of the deep ocean, where the faint rustle of prey or the distant clicks of a predator may be the only cues available. The lanternfish must also manage the oxygen content of its swim bladder, releasing gas slowly to avoid rupture and maintaining the precise buoyancy needed to hover at a specific depth without expending excessive muscular effort. This delicate balance of gas exchange is a marvel of evolutionary engineering, yet it places a metabolic burden on the fish that constrains the duration and depth of its daily migration. The mechanics of the ascent are even more demanding, requiring the fish to reverse the compression process and actively secrete gas into the swim bladder as it rises toward the surface. This secretion is not instantaneous. It depends on specialized gas glands that extract oxygen from the blood and pump it into the bladder, a process that can take hours and must be carefully timed to avoid surfacing with too little buoyancy. The rate of ascent is therefore constrained by the rate of gas secretion, and any deviation from the optimal schedule can leave the fish vulnerable to predation or wasted energy expenditure. Some species have evolved to rely more on lipid storage than on swim bladders, using fatty tissues to provide neutral buoyancy without the need for gas exchange, which reduces the energetic cost of vertical travel, but also limits the speed of ascent. This lipid-based buoyancy is particularly common in deep-sea squid and jellyfish, which lack swim bladders altogether and must rely on their body composition to maintain depth. The diversity of buoyancy strategies among Twilight Zone organisms reflects the varying pressures they face, from the need to evade predators to the precise alignment of their vertical position with the available food supply. The temperature gradient through the water column adds another layer of complexity to the migration mechanics. Surface waters are typically warmer than the Twilight Zone, and as the fish descends, it encounters a rapid drop in temperature that slows its metabolism and reduces its swimming speed. This thermal barrier is not a simple obstacle. It alters the viscosity of the water, the diffusion rates of gases, and the efficiency of biochemical reactions within the fish's tissues. The lanternfish must adjust its enzyme activity and membrane fluidity to maintain function in the cold, a process that requires additional energy and may limit the depth of its migration. Some species have evolved specialized proteins, such as antifreeze glycoproteins, to prevent ice crystal formation in the extreme cold of the deep ocean, though these are more common in polar regions than in the temperate Twilight Zone. The thermal stratification of the ocean also creates distinct layers of water with different densities, which can act as barriers to vertical movement, forcing the fish to expend more energy to cross them. These density gradients are particularly pronounced in regions where freshwater from rivers or melting ice caps reduces the salinity of the surface layer, creating a sharp pike-knock line that the fish must breach. The diel vertical migration is also influenced by the oxygen minimum zone, a layer of water with extremely low oxygen concentrations that can be lethal to most aerobic organisms. Many Twilight Zone species have evolved to tolerate these hypoxic conditions, but they must manage their oxygen consumption carefully during the migration. The lanternfish, for example, can reduce its metabolic rate by up to 50% when entering the oxygen minimum zone, relying on anaerobic metabolism for short periods to sustain its swimming. This ability to switch between aerobic and anaerobic pathways is a key adaptation that allows the fish to pass through the oxygen minimum zone without suffering permanent damage. However, the duration of this passage is critical, and the fish must time its ascent and descent to avoid prolonged exposure to hypoxia. The oxygen minimum zone is not a uniform layer. It varies in thickness and depth across different ocean basins, and the migratory behavior of lanternfish changes accordingly. In the eastern tropical Pacific, where the oxygen minimum zone is particularly shallow and intense, some species have shortened their vertical migration or abandoned it altogether, remaining in the surface waters year-round. This plasticity in migratory behavior is a testament to the adaptability of Twilight Zone organisms, but it also complicates efforts to model the global carbon cycle, as the amount of carbon transported to the deep ocean depends on the precise timing and depth of the migration. The sensory cues that guide the migration are still not fully understood, but recent research has revealed an intricate interplay of light, magnetic fields, and chemical gradients. The descent is triggered by the diminishing light at dusk, which is detected by the fish's pineal gland and photoreceptors in the skin, but the precise threshold of light that initiates the upward migration varies among species and even among individuals. Some lanternfish respond to a change in light intensity of as little as 1%, while others require a more dramatic shift, suggesting that the migration is not a simple reflex, but a decision based on internal state and external conditions. The Earth's magnetic field may also play a role, providing a directional reference that helps the fish maintain its bearing during the vertical journey. Laboratory experiments have shown that larval lanternfish can orient themselves to magnetic fields, but whether adults use this sense during the diel vertical migration is still a matter of debate. The chemical composition of the water, including the concentration of dimethyl sulfide and other volatile compounds, could serve as a guide, helping the fish locate patches of high productivity in the surface waters. These chemical cues are particularly important for species that feed on phytoplankton, which release dimethyl sulfide as a byproduct of their metabolism. The physical strain of the migration is not limited to the fish themselves. It also affects the water column, creating turbulence and mixing that can influence nutrient distribution and plankton growth. Each lanternfish, as it swims upward, induces a small-scale wake that stirs the water, and the aggregate effect of millions of migrating fish can generate significant vertical mixing. This biogenic mixing has been proposed as a mechanism for transporting nutrients from the deep ocean to the surface, potentially enhancing primary productivity in the Twilight Zone. However, the magnitude of this effect is still disputed, with some oceanographers arguing that the energy input from migrating fish is negligible compared to wind-driven mixing. The controversy highlights the difficulty of quantifying the impact of biological processes on the physical ocean, a challenge that requires both high-resolution modeling and direct measurements from autonomous vehicles. The deep-sea gliders that now patrol the Twilight Zone can detect the subtle changes in temperature and salinity caused by the movement of fish, providing a window into the mechanics of the migration that was previously impossible. The partial migration observed in some lanternfish populations reveals that not all individuals participate in the full vertical journey. Some fish remain in the Twilight Zone year-round, either because they are too small to compete for surface prey or because they have adopted a different feeding strategy that relies on detritus sinking from above. This partial migration is not a fixed trait. It can vary with the season, the availability of food, and the size of the fish. Larger individuals with their greater energy reserves are more likely to migrate to the surface, while smaller fish may remain at depth to avoid predation. The decision to migrate is also influenced by the risk of encountering predators in the surface waters, which may be higher during certain moon phases or in regions where the water is clear. The lanternfish must weigh the energetic cost of the ascent against the potential reward of a rich feeding ground, a calculation that is constantly updated based on sensory feedback. This individual variability makes the diel vertical migration a complex phenomenon, one that cannot be simplified into a single set of rules. The descent of the diel vertical migration is a testament to the adaptability of Twilight Zone organisms, which have evolved to exploit a narrow window of opportunity in the surface waters each night. The mechanics of this journey are still being unraveled, with each new study revealing more layers of complexity. The partial migration observed in some lanternfish is just one example of the variability that challenges our understanding. As scientists deploy more sophisticated instruments, such as deep-sea gliders and autonomous underwater vehicles, they are beginning to see that the migration is not a monolithic event, but a mosaic of individual decisions, each shaped by the unique physiology and experience of the organism. This revelation transforms the Twilight Zone from a simple layer of migrating animals into a dynamic, living system that is still full of unanswered questions. The exact mechanisms that govern the timing of the ascent, the depth of the descent, and the duration of the stay in the surface waters remain elusive, and each new data point from the ocean depths adds a new piece to the puzzle. The diel vertical migration is a daily reminder of the ocean's hidden rhythms, a pulse that connects the deep to the surface and that scientists are only beginning to understand. Far beneath the waves, in the Twilight Zone that begins at 200 meters and extends to 1,000, a hidden machinery operates with the quiet precision of a planetary heartbeat. This is the biological carbon pump, a system that transfers carbon from the sunlit surface ocean into the deep sea, where it can remain for centuries or millennia. The pump is driven entirely by life, by the daily activities of creatures that most people will never see, yet whose collective actions shape the climate of the entire Earth. The process begins in the euphotic zone, the uppermost layer where sunlight penetrates and photosynthesis flourishes. Tiny phytoplankton, single-celled plants that drift in the surface waters, absorb carbon dioxide from the atmosphere and convert it into organic carbon through photosynthesis. When these phytoplankton are consumed by zooplankton, or when they die naturally, their carbon-rich remains begin a slow descent into the darkness below. This falling organic matter, known as marine snow, provides the fundamental fuel for the entire Twilight Zone ecosystem. Mesopelagic organisms play a crucial role in accelerating and modifying this carbon transport. When lanternfish, bristlemouths, and other fish feed on zooplankton near the surface, they digest their prey and release fecal pellets that sink much faster than individual phytoplankton cells. These pellets are compact, dense, and often surrounded by a mucous membrane that protects them from bacterial decomposition during their fall. A single fecal pellet from a lanternfish can sink at rates of hundreds of meters per day, carrying carbon directly into the deep ocean before it can be recycled by surface microbes. Dead organisms also contribute significantly to the carbon pump. When a mesopelagic fish dies naturally, its body sinks through the water column, bypassing the shallow recycling zones and delivering a concentrated carbon payload to the seafloor. Even partial carcasses, such as the remains of a squid or a crustacean that has been partially consumed by a predator, continue to sink and deliver carbon to the depths. Scientists estimate that the combined contribution of fecal pellets, dead organisms, and other sinking particles removes between 4 and 12 billion tons of carbon from the surface ocean every year, transporting it through the Twilight Zone and into the abyss. Respiration at depth represents another important pathway for carbon export. Mesopelagic organisms that feed near the surface but spend their daylight hours in deeper waters undergo a daily cycle of vertical migration. When they return to the Twilight Zone after feeding, they respire, releasing carbon dioxide directly into the deep water. This carbon dioxide, produced by the metabolic activity of billions of fish, squid, and crustaceans, is effectively sequestered because the deep ocean circulates very slowly. A single molecule of carbon dioxide released at 800 meters may not return to the surface for hundreds of years. The magnitude of this carbon flux is staggering. The total carbon exported through the mesopelagic zone each year is roughly equivalent to the entire annual carbon emissions of the European Union. This biological pump operates continuously, day and night, without any human intervention, quietly pulling carbon out of the atmosphere and storing it in the ocean's interior. Without this process, the concentration of carbon dioxide in the atmosphere would be significantly higher than it currently is, and the rate of climate change would be far more severe. Understanding why this matters for global climate requires looking at the bigger picture. The ocean absorbs approximately 30% of all human-caused carbon dioxide emissions, roughly 10 billion tons every year. The biological carbon pump is one of the major mechanisms responsible for this absorption. Phytoplankton draw down carbon dioxide from the atmosphere during photosynthesis, and the sinking of organic matter transfers that carbon into the deep ocean, where it cannot easily escape back into the atmosphere. If the biological pump were to weaken or slow, the ocean's capacity to absorb carbon dioxide would diminish, and more of our emissions would remain in the air. The efficiency of the pump depends heavily on the health and activity of mesopelagic communities. When surface waters are rich in nutrients, phytoplankton blooms occur, and the subsequent rush of marine snow feeds a cascade of life in the Twilight Zone. This in turn increases the export of carbon to the deep sea. But when surface productivity declines, perhaps due to warming or changes in ocean currents, the entire system can become less effective. Scientists are only beginning to model these complex feedback loops, and many uncertainties remain about how the biological pump will respond to a rapidly changing climate. The food web connections between the mesopelagic layer and the surface ocean are intricate and far-reaching. Lanternfish, which are among the most abundant vertebrates on Earth, form the central hub of this network. These small fish, typically no more than 10 centimeters long, exist in vast numbers with a total biomass estimated at hundreds of millions of tons. They feed on copepods, krill, and other zooplankton in the surface waters at night, then descend to the Twilight Zone during the day, where they become prey for larger predators. Tuna, including skipjack, yellowfin, and big eye, dive into the upper Twilight Zone to hunt lanternfish and squid. These commercially valuable fish are top predators in the open ocean, and their dependence on mesopelagic prey links the carbon pump directly to human economies. When tuna consume lanternfish, they are essentially harvesting carbon that was initially captured by phytoplankton and transported into the deep by the daily migration of their prey. The health of tuna fisheries therefore depends on the same biological processes that regulate the global climate. Whales also rely heavily on the Twilight Zone food web. Sperm whales, which can dive to depths of over 1,000 meters, feed primarily on giant squid that inhabit the mesopelagic layer. Baleen whales, such as blue whales and humpbacks, feed on krill and other zooplankton in the surface waters, but those krill themselves depend on the daily migration of mesopelagic organisms for their own food supply. The movements of these great mammals across the ocean are intimately tied to the productivity of the Twilight Zone, and their presence influences the distribution of nutrients and carbon throughout the water column. Seabirds, including shearwaters, petrels, and albatrosses, also depend on mesopelagic prey. These birds can travel hundreds of kilometers from their nesting colonies to forage in productive ocean regions. They feed on lanternfish and squid that are brought to the surface by migrating predators or that rise to the surface during the night. The seabirds then return to their colonies, where they deposit guano rich in nitrogen and phosphorus, fertilizing coastal ecosystems and completing a cycle that connects the open ocean to the land. At the other end of the food web, deep-sea scavengers wait for the steady rain of organic matter from above. Fragments of carcasses, dislodged fecal pellets, and the remains of dead fish fall through the Twilight Zone and into the Midnight Zone below, where creatures such as amphipods, sea cucumbers, and brittle stars feed on this detritus. These scavengers play a vital role in processing the carbon that reaches the seafloor, consuming it and incorporating it into their own tissues or releasing it back into the water as dissolved organic matter. Without this scavenging community, the seafloor would become a stagnant repository of organic debris, and the carbon cycle would slow dramatically. Gelatinous zooplankton, including jellyfish, salps, and pyrosomes, occupy an underestimated role in the carbon flux of the Twilight Zone. These delicate, transparent creatures are often overlooked in oceanographic studies because they are difficult to capture with nets and dissolve rapidly when preserved. But their importance in the biological pump is becoming increasingly clear. Salps, for example, are filter feeders that strain phytoplankton and small particles from the water, producing large, dense fecal pellets that sink remarkably fast. A single salp can produce a fecal pellet that sinks at a rate of over 1,000 meters per day, far faster than the pellets of copepods or krill. This means that the carbon contained in a salp pellet can reach the deep ocean in a matter of hours, bypassing the Twilight Zone almost entirely. When salps bloom in vast numbers, as they sometimes do in response to phytoplankton blooms, they can export enormous quantities of carbon to the seafloor in a very short time. Some scientists estimate that salp blooms may account for a significant portion of the total carbon exported to the deep ocean in certain regions. Jellyfish, too, contribute to the carbon pump in ways that are still being studied. When jellyfish die, their bodies sink rapidly, carrying carbon directly to the seafloor. Unlike the slow, gradual descent of marine snow, a jellyfish carcass can fall hundreds of meters in a day, delivering a concentrated pulse of nutrients and carbon to the benthic community. This pulse can trigger feeding frenzies among deep-sea scavengers and temporarily alter the chemistry of the sediment. The role of jellyfish in the carbon cycle is particularly relevant because jellyfish populations are increasing in many parts of the ocean, possibly due to overfishing and climate change. Pyrosomes, which are colonial tunicates that form long, hollow cylinders, also play a role in the Twilight Zone. These creatures can grow to several meters in length and are capable of rapid vertical movement. They feed on phytoplankton and small particles, and their fecal pellets, like those of salps, sink quickly. Pyrosome blooms have been observed in the Pacific Ocean, and their impact on the carbon pump is an active area of research. The fact that these delicate organisms can survive in the cold, dark waters of the Twilight Zone is a testament to the adaptability of life in this mysterious environment. The carbon that passes through the Twilight Zone is not all exported to the deep ocean. A significant portion is recycled within the mesopelagic layer itself. Bacteria and other microorganisms consume organic matter in the water column, breaking it down and releasing carbon dioxide back into the water. This process, known as remineralization, returns carbon to the dissolved inorganic pool, where it can be transported by ocean currents or eventually returned to the surface through upwelling. The balance between export and recycling determines how much carbon is actually sequestered in the deep ocean. The Twilight Zone is a region of intense biological activity, and the organisms that live there are constantly processing, consuming, and transforming carbon. The average residence time of organic carbon in the mesopelagic zone is measured in days to weeks, compared to months to years in the surface ocean and centuries in the deep sea. This rapid turnover means that the mesopelagic zone is a bottleneck in the global carbon cycle, a place where carbon can either be sent to long-term storage or returned to the atmosphere through the respiration of organisms that migrate back to the surface. One of the great challenges for scientists is to accurately measure the amount of carbon that passes through the Twilight Zone. Traditional methods, such as sediment traps deployed from research vessels, provide only a partial picture of the flux. These traps can miss the largest and the smallest particles, and they cannot account for the active transport of carbon by migrating animals. New technologies, including autonomous underwater vehicles, acoustic sensors, and DNA sequencing of microbial communities, are beginning to reveal the true complexity of the carbon pump. The biological carbon pump is not a single uniform process, but a collection of interconnected pathways, each with its own timescale and efficiency. The contribution of fecal pellets, dead organisms, gelatinous zooplankton, and migrating fish all must be considered together to understand how carbon moves through the Twilight Zone. Models that simulate the global carbon cycle are increasingly incorporating these details, but they still rely on assumptions that are based on limited data. The Twilight Zone remains one of the least understood parts of the ocean, and the role of its inhabitants in the carbon pump is a subject of ongoing discovery. The implications of this research extend far beyond marine biology. The ability of the ocean to absorb carbon dioxide is a critical buffer against climate change, and any disruption to the biological pump could have profound consequences. If rising temperatures reduce the productivity of phytoplankton, or if changes in ocean chemistry harm the organisms that build carbonate shells, the entire system could shift. Some scientists have proposed geoengineering schemes to enhance the biological pump, such as adding iron to the ocean to stimulate phytoplankton blooms, but the risks and uncertainties of such interventions are immense. The Twilight Zone is a region of immense ecological and climatic importance, yet it remains largely unexplored. The creatures that live there, from the smallest bacteria to the largest jellyfish, are connected in a web of relationships that scientists are only beginning to map. Each organism, whether it is a lanternfish swimming through the depths or a salp filtering the water, plays a part in the great carbon conveyor belt that links the surface to the abyss. The health of this system is directly tied to the health of the planet, and understanding how it works is one of the most urgent scientific challenges of our time. Every night, the Twilight Zone becomes the stage for the largest animal migration on Earth. An estimated 10 billion tons of marine organisms rise from the depths toward the surface, feeding on phytoplankton under the cover of darkness, then retreating before dawn to avoid visual predators. This vertical migration is a fundamental ecological rhythm that drives the biological carbon pump, as these creatures consume carbon near the surface and transport it downward in their bodies and waste. The migration is not a random movement, but a finely tuned response to light, temperature, and predation risk, and it involves species from microscopic copepods to meter-long lanternfish. The copepods themselves form the backbone of this migration, with some species undertaking daily journeys of hundreds of meters. These crustaceans feed on plankton in the surface waters and then descend to the Twilight Zone, where they are consumed by larger predators or die and sink. Their fecal pellets, dense and compact, fall rapidly through the water column, carrying carbon deep into the abyss. Scientists have calculated that the collective daily migration of copepods alone moves more carbon than all the rivers of the world transport in solution. The euphausiids, or krill, also play a critical role in the Twilight Zone food web. Swarms of krill migrate vertically, and their grazing pressure can strip the surface of phytoplankton in a matter of hours. When they descend, they become prey for squid, fish, and even whales that venture into the mesopelagic zone. The carbon contained in their bodies, if not consumed, may sink to the seafloor as carcasses, locking away that carbon for centuries or longer. Lanternfish, which are among the most abundant fish in the ocean, are the primary vertebrate migrators. These small, bioluminescent fish possess swim bladders that allow them to adjust their buoyancy as they travel between depths. They feed on copepods and krill at the surface, then return to the Twilight Zone to digest and avoid predation. Their fecal pellets, often larger and more cohesive than those of smaller zooplankton, sink at higher speeds, contributing disproportionately to the downward flux of carbon. The migration itself is energetically costly, and organisms must balance the gain of feeding at the surface with the risk of being eaten. This trade-off shapes the entire ecology of the Twilight Zone, creating a dynamic where predators and prey are constantly adjusting their positions. Some species, such as certain jellyfish, remain in the Twilight Zone permanently, feeding on the falling marine snow and the occasional migrant that becomes trapped in their tentacles. Marine snow is the continuous rain of organic debris that falls from the surface into the Twilight Zone. It consists of dead phytoplankton, fecal pellets, mucus, and the discarded feeding structures of gelatinous organisms. As this material descends, it is consumed by a diverse community of bacteria, protists, and small animals, which break it down and release nutrients back into the water. This process, known as the microbial loop, recycles carbon and nutrients within the Twilight Zone, limiting the amount that reaches the deep sea. The efficiency of the biological carbon pump depends on the composition and aggregation of marine snow. When particles are large and dense, they sink quickly, bypassing the Twilight Zone. But when they are small and slow, they are more likely to be consumed by microbes and zooplankton, releasing carbon as dissolved organic matter that can be carried back to the surface by upwelling currents. Scientists are working to understand how changes in the Twilight Zone community alter this balance, and the results are critical for predicting future carbon storage. Viruses are another unexpected force in the Twilight Zone ecology. They infect bacteria and phytoplankton, causing them to burst and release their organic contents into the water. This process, called viral shunt, diverts carbon away from the microbial loop and into the dissolved pool, where it can be more easily recycled. Estimates suggest that viruses kill up to 20% of the microbial biomass in the ocean each day, and their role in the Twilight Zone is just beginning to be explored. The impact of oxygen minimum zones on the Twilight Zone is profound and growing. In many regions, particularly in the Pacific and Indian Oceans, the Twilight Zone contains a layer of water with very low oxygen levels. This oxygen minimum zone forces many organisms to migrate in a narrow band, avoiding the depths where oxygen is too low for their metabolism. Some species have evolved adaptations such as larger gill surfaces or the ability to produce hemoglobin to survive in these hypoxic waters. But as climate change reduces oxygen solubility and increases stratification, these oxygen minimum zones are expanding, squeezing the Twilight Zone habitat. The compression of habitable space alters predator-prey interactions and the efficiency of the biological pump. Migrating organisms may have to travel farther to reach sufficient oxygen, increasing their energy expenditure and reducing their reproductive output. In some areas, the stress of low oxygen has been linked to mass die-offs of gelatinous zooplankton, which then sink rapidly, creating a large pulse of carbon to the sea floor. This pulse can overload the benthic ecosystem, leading to anoxic conditions on the seafloor itself. Gelatinous zooplankton, including salps, jellyfish, and siphonophores, are often overlooked in studies of the Twilight Zone, but they are increasingly recognized as major players. Salps, in particular, form long chains that can stretch for meters, and they filter huge volumes of water, consuming phytoplankton and bacteria. Their fecal pellets are exceptionally large and dense, sinking at rates of hundreds of meters per day, which makes them highly efficient vectors for carbon transport. During blooms, salps can remove significant amounts of carbon from the surface and deliver it to the deep sea within days. Jellyfish, on the other hand, are predators that feed on copepods, fish larvae, and other gelatinous organisms. They are not strong migrators, but many species move vertically in response to prey or to avoid turbulence. When jellyfish die, their bodies decompose slowly and can sink to the seafloor, providing a food source for deep-sea scavengers. The carbon from jellyfish carcasses is often less dense than from other sources, but it still contributes to the overall flux. Siphonophores, which are colonial cnidarians, are among the longest animals in the ocean, with some species reaching lengths of over 40 meters. They drift in the Twilight Zone, trailing stinging tentacles that capture small fish and crustaceans. Their feeding exerts a top-down control on the migrant population, and their own biomass, when it dies, sinks to the deep sea. The complex life cycles of these organisms, including alternating generations of medusae and polyps, add another layer of ecological complexity. The Twilight Zone also hosts a vast diversity of microbial life, including archaea, bacteria, and viruses that are adapted to low light and high pressure. These microorganisms are the primary decomposers of marine snow, and they also fix carbon through chemosynthesis in the dark. Some bacteria in the Twilight Zone are capable of using the energy from sinking organic matter to produce new biomass, which then becomes part of the microbial loop. The rates of microbial activity in the Twilight Zone are lower than in the sunlit surface, but the sheer volume of water means that the total microbial processing is immense. The role of zooplankton fecal pellets cannot be overstated. The size, shape, and density of these pellets determine how far they sink before being consumed or broken down. Copepod pellets are often small and slow, while euphausiid pellets are larger and faster. The gelatinous houses of appendicularians, which are discarded and replaced daily, are also a significant component of marine snow. These houses, made of a mucus-like substance, can trap particles and become a fast-sinking vehicle for carbon. The Twilight Zone is not a uniform environment. It is structured by physical gradients of temperature, salinity, and density, which create layers of water with different ecological properties. The sharp thermocline at the base of the Twilight Zone can act as a barrier, preventing some sinking particles from reaching the deep sea. Internal waves and eddies can mix the water, bringing nutrients upward and oxygen downward, creating patches of high productivity. These physical dynamics are chaotic and difficult to predict, adding another layer of uncertainty to carbon flux models. The organisms of the Twilight Zone have evolved a remarkable array of sensory adaptations. Many species have large eyes to capture the faint bioluminescent flashes of their prey, or to detect the silhouettes of predators above. Others rely on chemoreception, following the scent of food or the chemical signals of danger. The Twilight Zone is a world of subtle cues, where a single photon or a trace molecule can mean the difference between life and death. Bioluminescence itself is a central ecological feature of the Twilight Zone. The majority of species in this region are capable of producing light, using it for everything from attracting mates to startling predators to counter-illumination, where animals match the downwelling light from the surface to hide their silhouette. The patterns of bioluminescence vary with depth, time of day, and season, and scientists are only beginning to decode the language of these glowing signals. The seasonal variation in the Twilight Zone is driven by the cycle of phytoplankton blooms at the surface. In spring, when nutrients are abundant and light increases, phytoplankton populations explode, leading to a pulse of organic matter that sinks into the Twilight Zone. This pulse triggers a cascade of responses, from bacterial blooms to increased zooplankton reproduction. The timing and magnitude of these pulses are highly variable, and they are influenced by climate phenomena such as El Niño and the North Atlantic Oscillation. The long-term monitoring of the Twilight Zone is extremely difficult due to the depth and the need for specialized equipment. Research vessels equipped with nets, sonar, and water samplers can only capture snapshots of this dynamic ecosystem. Autonomous underwater vehicles and profiling floats are beginning to provide continuous data, but they are limited in their ability to capture the full diversity of life. The development of new technologies, such as advanced imaging systems and genetic sensors, is essential for understanding the ecological processes that govern the carbon pump. One of the most pressing questions is how the Twilight Zone will respond to ongoing climate change. Ocean warming is expected to reduce the solubility of oxygen and increase stratification, which may shrink the habitable zone for many migrators. Acidification, caused by the absorption of carbon dioxide, can impair the ability of calcifying organisms like pteropods and foraminifera to build their shells, potentially reducing the flux of calcium carbonate to the deep sea. These changes are not independent. They interact with each other and with the dynamics of the food web. The ecological consequences of a weakened biological pump are severe. If less carbon reaches the deep sea, more remains in the surface ocean, where it can be returned to the atmosphere as carbon dioxide. This would create a positive feedback loop, accelerating climate change. The Twilight Zone, which currently stores an estimated 1 to 2 billion tons of carbon each year, could become a net source of carbon rather than a sink. Scientists are racing to model these feedbacks, but the uncertainties are enormous. The Twilight Zone is also a reservoir of genetic and biochemical diversity that remains largely untapped. The enzymes produced by deep-sea bacteria, adapted to high pressure and low temperature, have potential applications in biotechnology and medicine. The bioluminescent proteins of jellyfish and fish are already used as markers in biological research. The discovery of new species in the Twilight Zone continues at a steady pace, each one offering a glimpse into the evolutionary strategies that allow life to thrive in the dark. The interconnectedness of the Twilight Zone with the surface and the deep sea means that any change in this region will ripple outward. The fate of the Twilight Zone is tied to the health of the entire ocean, and the health of the ocean is tied to the stability of the climate. Understanding the ecology of this hidden world is not merely a scientific curiosity, it is a necessity for the survival of the planet as we know it. The creatures that live there, from the smallest bacteria to the largest jellyfish, are performing a silent service that sustains life above. The Twilight Zone is not a uniform layer, but a complex mosaic of depth strata, each with its own light gradient, temperature, and pressure. The vertical stratification of the water column creates distinct ecological niches, and the organisms that inhabit these depths are finely tuned to the specific conditions of their chosen layer. The sunlit surface waters above produce organic matter through photosynthesis, but only a fraction of this material makes its way into the Twilight Zone. The rest is consumed or decomposed in the upper layers, and the efficiency of this transfer depends on the size and composition of the particles. The biological carbon pump relies heavily on the formation of marine snow, a constant rain of organic debris, fecal pellets, and dead organisms. This material sinks slowly, taking days to weeks to reach the Twilight Zone, and during its descent it is subject to constant degradation by bacteria and other microbes. The smaller particles are more easily consumed, while larger, denser aggregates tend to sink faster and transport more carbon to depth. The gelatinous zooplankton, such as salps and larvaceans, play a crucial role in this process by producing fast-sinking fecal pellets and mucus houses that can carry carbon to the seafloor in a matter of hours. The diel vertical migration of zooplankton is the most conspicuous daily movement of biomass on Earth. Every evening, billions of tiny crustaceans, such as copepods and krill, ascend from the Twilight Zone to feed in the surface waters under the cover of darkness. They return to the depths at dawn, carrying with them the carbon they have consumed in the form of respired CO2 and fecal pellets that sink even deeper. This active transport of carbon is estimated to account for a significant portion of the total carbon flux to the deep ocean, and it is a direct result of the ecological interactions between predators and prey. The predators of the Twilight Zone are themselves adapted to the low light and high pressure of their environment. Lanternfish, with their rows of bioluminescent photophores, are among the most abundant vertebrates on Earth, and they form the backbone of the mesopelagic food web. They feed on the migrating zooplankton and in turn are preyed upon by larger fish, squid, and marine mammals. The energy flow through this layer is immense, but it is also inefficient, as most of the organic matter is respired or recycled within the Twilight Zone rather than exported to the deep sea. The microbial loop is a critical component of the Twilight Zone ecology, driving the breakdown of organic matter and the recycling of nutrients. Bacteria and archaea consume the dissolved organic carbon released by the fragmentation of sinking particles, and they respire much of this carbon back to CO2. This process, known as remineralization, occurs most rapidly in the upper Twilight Zone, where temperatures are higher and microbial activity is more intense. The balance between remineralization and export determines the depth at which carbon is sequestered, and this balance is sensitive to changes in temperature, oxygen, and the availability of fresh organic matter. The role of viruses in the Twilight Zone is only beginning to be understood, but it is clear that they are major players in the microbial loop. Viruses infect and lyse bacterial cells, releasing their contents into the surrounding water and creating a pool of dissolved organic matter that can be consumed by other microbes. This viral shunt diverts carbon away from the grazing food web and accelerates the recycling of nutrients within the Twilight Zone. The viral community is highly diverse and dynamic, and its activity is influenced by the abundance of bacteria and the availability of resources. The sinking particles that arrive in the Twilight Zone are not uniform in composition. They include fecal pellets from zooplankton, the remains of phytoplankton, and the mucus webs of gelatinous organisms. The size and density of these particles affect their sinking speed, and the presence of mineral ballast, such as calcium carbonate or silica, can increase their density and help them reach greater depths. The carbon content of these particles is also variable, and some particles are more resistant to microbial degradation than others. The recalcitrant organic matter that survives the journey through the Twilight Zone may eventually reach the seafloor, where it is buried in the sediments. The larvaceans, or appendicularians, are small, jelly-like organisms that build intricate mucus houses to filter food from the water. These houses are abandoned and replaced several times a day, and the discarded houses sink rapidly, carrying with them a load of trapped organic particles. This process is known as the mucus carbon pump, and it is a major pathway for the rapid export of carbon to the deep sea. The houses are colonized by bacteria and other microbes as they sink, and they provide a concentrated source of food for the organisms that live in the Twilight Zone. The ideal vertical migration of zooplankton is not a simple up and down movement. It is a complex choreography in which different species and life stages migrate to different depths, creating a layered structure of trophic interactions. The larger predators, such as the dragonfish and the hatchetfish, tend to remain at greater depths during the day, while the smaller zooplankton ascend to the surface. This ladder of migration allows for a more efficient transfer of energy, as each level of the food web taps into the resources brought up from below. The mesopelagic fish, particularly the lanternfish, are estimated to have a global biomass that rivals that of all other fish combined. However, recent studies using acoustic surveys have revised these estimates downward, suggesting that the biomass may be less than previously thought. Even so, the role of these fish in the carbon cycle is significant. They respire carbon dioxide at depth, and they produce fecal pellets that sink rapidly. They also undergo ideal vertical migrations, and their movement contributes to the transport of carbon from the surface to the Twilight Zone. The oxygen minimum zones of the ocean occur at depths where the decomposition of organic matter consumes oxygen faster than it can be replenished. These zones are expanding in many parts of the world due to climate change, and this expansion has profound implications for the ecology of the Twilight Zone. The organisms that live in oxygen minimum zones must be adapted to low oxygen levels, and they often have reduced metabolic rates and specialized respiratory systems. The lack of oxygen slows the rate of microbial decomposition, allowing more organic matter to sink through these zones and reach the deep ocean. The seasonal cycle of primary production in the surface ocean drives a pulse of carbon into the Twilight Zone. During the spring bloom, when phytoplankton growth is at its peak, the flux of sinking particles increases dramatically. The Twilight Zone responds to this pulse with a burst of biological activity, as the microbes and zooplankton consume the fresh organic matter. The timing and magnitude of this pulse can vary from year to year, and it is influenced by climate patterns such as El Niño and the North Atlantic Oscillation. The long-term changes in the frequency and intensity of these blooms will affect the amount of carbon that is sequestered in the deep ocean. The ecological interactions within the Twilight Zone are not limited to the consumption of sinking particles. The organisms that live there are also involved in mutualistic and symbiotic relationships. Many species of fish and squid host bioluminescent bacteria that produce light, which is used for counter-illumination, camouflage, or attracting prey. The bacteria benefit from the nutrients provided by their host, and the host benefits from the light. These symbioses are ancient and widespread, and they are a key part of the Twilight Zone ecology. The food web of the Twilight Zone is a complex network of feeding relationships that extends from the smallest bacteria to the largest predators. The gelatinous zooplankton, such as the comb jellies and the siphonophores, are often overlooked but are important components of this web. They are capable of capturing prey many times their own size, and they are themselves preyed upon by fish and turtles. The siphonophores, which are colonial organisms, can form long chains that drift through the water, trailing stinging tentacles that ensnare small crustaceans and fish. The role of the Twilight Zone in the global carbon cycle is not yet fully quantified, but it is clear that it is a crucial link between the surface and the deep ocean. The efficiency of the biological carbon pump depends on the depth at which carbon is remineralized, and the Twilight Zone is the region where most of this remineralization occurs. If the efficiency of the pump decreases, more carbon will remain in the surface waters, where it can be exchanged with the atmosphere. If it increases, more carbon will be stored in the deep ocean for centuries or millennia. The ongoing changes in the ocean, including warming, acidification, and deoxygenation, are already affecting the Twilight Zone. The temperature of the water influences the metabolic rates of the organisms, and warmer temperatures increase the rate of microbial decomposition. This could lead to a shallower remineralization depth, reducing the amount of carbon that reaches the deep ocean. The acidification of the water can affect the calcium carbonate shells of some plankton, making them more soluble and less likely to sink as ballast. The future of the Twilight Zone is uncertain, but the ecological and biogeochemical processes that take place there are essential for the stability of the climate. The creatures that inhabit this hidden world, from the tiny bacteria to the massive jellyfish, perform a silent service that sustains life above. The carbon they transport and the nutrients they recycle are part of a delicate balance that has been maintained for millions of years. The Twilight Zone is not a passive receiver of the surface's bounty, but an active participant in the global cycles that make the ocean a living system. The ocean's Twilight Zone holds a staggering number of fish, yet no one can agree on just how many. Acoustic surveys, which use sound waves to detect the density of animals in the water column, routinely produce estimates that are 10 times larger than those derived from net tows. This discrepancy is not a minor calibration error, but a fundamental rift in our understanding of the mesopelagic realm. The difference between the two methods suggests that the vast majority of fish in this layer are simply not captured by traditional sampling gear. The net avoidance problem lies at the heart of this uncertainty. Early researchers assumed that fish would be caught in roughly the same proportions as they were detected by sonar, but modern observations have revealed a startling truth. Many species are capable of detecting the approach of a net and actively swimming aside, often by several meters, to avoid being scooped up. This behavior means that the nets are selectively sampling only the slowest or most confused individuals, not the true community. The implications of this flaw are profound for any attempt to census the Twilight Zone. If the fish that are caught represent only a small and biased fraction of the total population, then every model built on net-derived data is built on a foundation of sand. Scientists have begun attaching cameras to trawl nets, and the footage shows a constant stream of fish darting out of the path of the mesh. These observations confirm that the net is not a passive collector, but an active disturbance that animals can evade. The percentage of mesopelagic species that remain undescribed is shockingly high. Current estimates suggest that up to 50% of the fish species in the Twilight Zone have never been formally named or cataloged by science. This is not a situation where a few rare creatures are missing from the ledger. It means that half of the biodiversity in this vast habitat is essentially unknown. Each new deep-sea expedition brings back specimens that do not match any existing description, and genetic analysis often reveals that what was once thought to be a single species is actually a complex of several distinct forms. The discovery of such a large hidden diversity changes the way we think about the resilience of the ecosystem. If we do not know what lives there, we cannot predict how it will respond to change. The traditional methods of taxonomy, based on physical characteristics, are being supplemented by DNA barcoding, but the pace of discovery is still far slower than the rate of potential exploitation. The unknown species are not just curiosities, they are the functional components of a system that we are only beginning to grasp. Industry proposals to harvest mesopelagic fish as fish meal represent a direct confrontation with this uncertainty. Several nations have explored the commercial potential of catching lanternfish and other small mesopelagics in huge quantities, grinding them into feed for aquaculture and livestock. The logic is simple. The biomass appears enormous, so even a modest harvest could supply a growing demand for protein. But the logic is flawed because the underlying census is uncertain, and the ecological roles of these fish are poorly understood. The ecological risks of such a harvest are severe and largely unquantified. Mesopelagic fish are the primary consumers of zooplankton and the primary prey for larger predators, including tuna, squid, and marine mammals. Removing a large portion of this intermediate layer could collapse the food web in ways that cascade upward and downward. The fish also transport carbon from the surface to the deep ocean through their daily migrations, and a reduction in their numbers could alter the global carbon cycle. Climate change is now adding another layer of complexity to the mystery of the Twilight Zone. The oxygen minimum zone, a layer of water where dissolved oxygen levels are extremely low, is expanding in many parts of the ocean. As the ocean warms, it holds less oxygen, and the zone is predicted to become both shallower and thicker in the coming decades. This shift directly affects the daily vertical migration of mesopelagic animals, many of which are already living near the edge of their physiological tolerance. The fundamental mystery is that the behavior of some deep scattering layers does not match any existing model of how animals should respond to changing oxygen levels. In some regions, the layer splits into two distinct bands at night, with one group migrating into the surface waters and another staying at greater depth. No current model based on temperature, light, or oxygen can explain why some individuals choose to remain in the darker, colder water while others ascend. The pattern suggests that unknown biological factors, such as predator avoidance or competition, are overriding the simple environmental cues. The consequence of these unknowns is a growing sense that the Twilight Zone is not a stable, predictable environment, but a dynamic system that we are only beginning to observe. The scientific community is left with more questions than answers, and each new study seems to reveal another layer of complexity. The net avoidance behavior, the undescribed species, the uncertain biomass, and the unpredictable responses to climate change all point to the same conclusion. The Twilight Zone is a frontier where the gaps in our knowledge are far larger than the islands of certainty. The Twilight Zone remains a vast unknown, precisely because each new observation raises deeper questions about the mechanisms that govern life in this dimly lit realm. Scientists have documented that the deep scattering layer sometimes fragments into multiple smaller layers at different depths. Yet no single environmental variable can predict when or why this fragmentation occurs. The phenomenon suggests that social interactions or unseen chemical cues may be driving the animals to form distinct aggregations in the darkness. Some researchers have proposed that these secondary layers represent different species sorting themselves by their preferred prey, but the actual composition of these layers often defies identification using net samples or acoustic data. The result is a persistent uncertainty about whether the Twilight Zone functions as a single interconnected community or as a collection of isolated populations that rarely interact. One of the most perplexing unexplained features of the Twilight Zone is the existence of what oceanographers call phantom layers, acoustic reflections that appear suddenly in the middle of the night and vanish just as quickly without any apparent migration pattern. These ephemeral scatters have been recorded in the Gulf of Mexico and the eastern tropical Pacific, yet they do not correspond to any known species or behavior. The sound returns from these layers often show a frequency signature that is unlike any fish or squid, leading some to speculate that they might be caused by enormous aggregations of gelatinous organisms that are too fragile to be caught by nets. The alternative explanation, that these are simply instrument artifacts, has been ruled out by repeated observations from multiple research vessels and autonomous gliders. The mystery deepens because these phantom layers sometimes appear in regions where the oxygen concentration is so low that most fish cannot survive, suggesting that the organisms responsible may possess unknown physiological adaptations. The bioluminescent displays of the Twilight Zone also harbor many unexplained patterns. While scientists understand that many creatures produce light for communication, camouflage, or predation, the sheer variety and complexity of these flashes remain poorly cataloged. Observations from submersibles have revealed synchronized pulses of light that sweep across hundreds of meters of water, resembling a slow-moving wave of fire in the dark. The function of these coordinated displays is unknown, and no proposed hypothesis, whether it is a mating ritual, a predator confusion tactic, or a form of long-distance signaling, has been confirmed by experimental evidence. The timing of such displays often correlates with the lunar cycle, but the exact mechanism that links moonlight to bioluminescent behavior in the deep sea is not understood. Some researchers have suggested that the moonlight itself may be detected by animals that have migrated to the surface, but the signal must then be transmitted downward through the water column, a process that remains entirely speculative. The life cycles of many Twilight Zone organisms remain undocumented, and this gap in knowledge prevents scientists from understanding how populations are sustained over time. For example, the larvae of lanternfish, the most abundant fish in the mesopelagic zone, are rarely found in the same depths as the adults, and their development and settlement patterns are largely unknown. Similarly, the reproduction of the vampire squid, Vampiroteuthis infernalis, has never been observed in the wild, and the only specimens ever collected with eggs were found in such poor condition that their reproductive biology remains a mystery. The absence of basic life history information means that scientists cannot estimate how fast these populations can recover from disturbances, such as fishing pressure or climate change. Without this knowledge, any model of the Twilight Zone's role in the global carbon cycle is built on assumptions that may be fundamentally flawed. The phenomenon of marine snow, the continuous rain of organic particles from the surface to the deep, is another area where the Twilight Zone presents more questions than answers. While the general process is understood, the rates at which these particles are consumed, repackaged, and remineralized by mesopelagic organisms are highly uncertain. Observations from sediment traps and underwater cameras have shown that the particles can be swiftly colonized by bacteria and small zooplankton, but the exact fate of the carbon they carry is difficult to trace. The Twilight Zone is often described as a filter that determines how much carbon reaches the deep ocean, yet the efficiency of this filter varies dramatically with location and season. Scientists have found that in some regions, nearly all of the sinking carbon is consumed within the Twilight Zone, while in others, a significant fraction passes through to the abyss. The factors that control this variability, whether it is temperature, oxygen, or the composition of the microbial community, are not well understood, and the current generation of climate models cannot reproduce these patterns reliably. The oxygen minimum zones that intersect the Twilight Zone at certain depths are environments where the unknowns are especially acute. In these regions, oxygen levels fall below 0.5 milliliters per liter, a concentration that is lethal for most fish. Yet some species, such as certain lanternfish and bristlemouths, are found in these zones in surprisingly high numbers. How these animals survive the low oxygen conditions is a puzzle, because their metabolic rates are not significantly lower than those of fish living in well-oxygenated waters. Some researchers have proposed that these fish have evolved special hemoglobin that binds oxygen more tightly, but direct measurements of their blood chemistry are rare. The behavior of these fish within the oxygen minimum zones is also puzzling. Acoustic surveys show that they often congregate at the very edge of the hypoxic layer, as if they are balancing between the need to feed and the need to avoid even lower oxygen levels. The exact threshold that triggers their vertical movements is unknown, and it is unclear how they will respond if the oxygen minimum zones expand due to climate change. The role of viruses in the Twilight Zone is another frontier that remains almost entirely unexplored. Marine viruses are known to be the most abundant biological entities in the ocean, and they can infect and kill up to 20% of the ocean's bacteria each day. In the Twilight Zone, the viral community is thought to be different from that in surface waters, but the diversity and function of these viruses are virtually unknown. Some studies have suggested that viruses may play a key role in the rapid cycling of organic matter at depth because they can cause cells to burst and release their contents into the water without the need for predation. However, the rates of viral infection in the Twilight Zone have never been measured directly, and the impact of viral lysis on the carbon flux is a major unknown. The possibility that viruses might also infect mesopelagic fish and squid has not been investigated, raising the question of whether diseases could be a significant source of mortality in the deep sea. The strange predator-prey relationships of the Twilight Zone are also poorly understood, particularly because many of the animals possess adaptations that make them invisible to conventional observation. For instance, the barrel-eye fish, Macropinna microstoma, has a transparent head that allows it to see upward through its own skull, presumably to detect the silhouettes of prey against the faint light from the surface. Yet the exact prey of this fish is unknown, because its stomach contents are rarely examined, and its feeding behavior has only been observed a handful of times from deep-sea submersibles. The same uncertainty applies to many other mesopelagic species, such as the dragonfish, which use red bioluminescence to illuminate prey that cannot see red light, but the effectiveness of this strategy in the wild has never been quantified. The unknown interactions between predators and prey mean that the Twilight Zone's food web is a sketch rather than a detailed map, with many lines and arrows that are drawn from inference rather than direct evidence. The phenomenon of the missing biomass in the Twilight Zone is one of the most persistent mysteries. Theoretical calculations based on primary production in the surface ocean suggest that the Twilight Zone should contain far more carbon than what is actually measured by nets and acoustics. This discrepancy, sometimes called the mesopelagic biomass paradox, has led some scientists to propose that the existing methods of sampling are missing a large fraction of the biomass, possibly because the animals are too fragile to be caught or too small to be detected by sonar. Others have suggested that the missing biomass might be in the form of free-floating microbial aggregates or even unknown life forms that are not recognized by current techniques. The size of the discrepancy is enormous. Estimates range from a factor of 2 to an order of magnitude, and the uncertainty casts doubt on all calculations of the Twilight Zone's role in the global carbon budget. Until the missing biomass is found and accounted for, the Twilight Zone will remain a black box in the Earth's climate system. The unpredictability of the Twilight Zone's response to climate change is the final, overarching unknown that ties all these puzzles together. Models that attempt to simulate the future of the ocean's carbon cycle must include the Twilight Zone, but they do so with parameters that are based on scant data. The warming of the surface ocean is expected to reduce the amount of oxygen that can be dissolved in the water, which will likely expand the oxygen minimum zones and compress the habitable depth range for many mesopelagic species. Yet the actual response of the Twilight Zone's organisms to these changes is unknown, because their physiological tolerances have been measured for only a handful of species. The possibility that the Twilight Zone could shift from a carbon sink to a carbon source, releasing millennia of stored carbon back into the atmosphere, is a concern that cannot be dismissed. The frontier of the Twilight Zone is not merely a scientific curiosity. It is a region where the gaps in our knowledge could have profound consequences for the future of the planet. Each new study reveals another layer of complexity, and the islands of certainty remain small and scattered across a vast ocean of uncertainty. The Twilight Zone remains a realm where the simplest questions often yield the most complex and incomplete answers. Scientists have known for decades that countless organisms rise from the depths each night to feed in the surface waters, only to descend again before dawn. Yet the precise mechanisms that trigger this vertical migration and the navigational cues that allow these creatures to travel hundreds of meters in complete darkness remain largely unexplained. The sun's changing light intensity is thought to be the primary signal, but recent observations reveal that some species begin their ascent before the sun sets, and others linger in the upper layers long after the surface has brightened. This suggests an internal clock calibrated by factors beyond mere light, such as the Earth's magnetic field or subtle shifts in water pressure. But no single theory has been confirmed. The Great Deep Scattering Layer, a sonar-detected carpet of life that stretches across the world's oceans, is itself a phenomenon that defies simple explanation. When sonar was first developed during World War II, naval operators were baffled by a false seafloor that appeared to rise and fall with the day and night. This phantom bottom was eventually identified as the daily migration of billions of fish, squid, and crustaceans, but the layer's internal structure remains poorly understood. Acoustic surveys show that the scattering layer is not a uniform cloud, but a series of overlapping strata, each with its own density and composition. Some layers move at different speeds, some split apart, and others merge in ways that seem to contradict known predator-prey relationships. The reason for this complex layering is unknown, and it may reflect a hidden social organization or a response to subtle gradients in temperature and oxygen that are currently impossible to measure at the necessary resolution. Bioluminescence, the production of light by living organisms, is one of the most common but least understood phenomena in the Twilight Zone. Nearly every creature that lives there, from microscopic dinoflagellates to the giant squid, possesses the ability to produce light. The flashes and patterns observed are not random. They are used for startling predators, attracting mates, or luring prey. But the full vocabulary of this language of light remains untranslated. Scientists have recorded sequences of flashes that repeat with precise timing, suggesting a form of communication that may be as complex as the songs of birds or the calls of whales. Yet the lack of any observable receiver in the darkness makes it impossible to know whether these signals are directed at other individuals of the same species or at an entirely different audience. The possibility that bioluminescence serves as a kind of chemical or visual coordination across vast distances, perhaps aiding in the assembly of spawning aggregations or the detection of prey, is a hypothesis that cannot be tested with current technology. The life cycles of many Twilight Zone creatures are also steeped in mystery. The vampire squid, a species that inhabits the oxygen minimum zones, has a reproductive strategy that is unlike any other known cephalopod. It undergoes a single prolonged spawning event that lasts for months, during which the female releases eggs continuously while slowly deteriorating. The triggers for this process, the cues that signal the onset of maturity, and the fate of the young are all unknown. Juvenile vampire squids are almost never seen in the wild, suggesting that they occupy a different depth range or a different ecological niche than the adults. The same is true for many gelatinous animals, such as the siphonophores, which can grow to lengths of over 40 meters. These fragile colonial organisms fragment easily, and it is unclear whether the pieces can regenerate into new individuals or whether they simply die. The entire life history of the most abundant animal on Earth, the bristlemouth fish, remains a black box. These fish, which number in the quadrillions, are known to have a short lifespan of about 1 year, but the details of their spawning, their larval development, and their mortality rates are all based on extrapolations from a tiny number of samples. The role of marine snow, the constant rain of organic debris from the surface, is another critical unknown. This material, composed of dead plankton, fecal pellets, and other detritus, is the primary source of food for the Twilight Zone. But the rate at which it is consumed, the efficiency with which it is repackaged, and the portion that escapes to the deep sea are all poorly constrained. Recent studies using sediment traps have shown that the composition of marine snow changes dramatically with depth, suggesting that it is processed by a succession of different organisms. Some of these organisms are known to produce mucus nets or sticky appendages that capture the particles, but the identity of the most efficient consumers remains a mystery. The microbial community that lives on and within these particles is even less understood. Bacteria and archaea break down the organic matter, releasing dissolved nutrients and also consuming oxygen, but the speed and extent of this decomposition are influenced by factors that are not yet mapped. The result is that the carbon budget of the Twilight Zone, the balance between what is consumed, what is exported, and what is respired, is a calculation with large error bars. The acoustic environment of the Twilight Zone, a world of clicks, grunts, and whistles, is only beginning to be explored. Many fish and marine mammals produce sounds that travel for kilometers through the water column, but the Twilight Zone is also home to a vast array of snapping shrimp and other invertebrates that create a constant, low-frequency hiss. This background noise may interfere with the communication of other species, or it may be used as a form of passive sonar by predators. The deep scattering layer itself is a source of sound, as the gas bladders of fish resonate when they are exposed to the pressure changes of passing ships or natural events. These acoustic signatures could be used to monitor the biomass and behavior of the Twilight Zone, but the interpretation of the signals is still in its infancy. The possibility that there are unknown vocalizations, perhaps from giant squid or deep-sea jellyfish, that have not been detected because of the limited frequency range of our hydrophones, is a tantalizing prospect. The genetic diversity of the Twilight Zone is another frontier that remains largely unexplored. The few genetic studies of mesopelagic fish have revealed the existence of cryptic species, organisms that look identical but are genetically distinct. This suggests that the true number of species in the Twilight Zone may be far higher than the current estimate of several 100,000. Each new RNA or DNA sample from the deep ocean contains sequences that do not match any known organism, hinting at a vast hidden biodiversity. Some of these unknown organisms may be capable of producing novel enzymes or compounds that could be used in medicine or biotechnology. The Twilight Zone is a potential treasure trove of bioactive molecules, but the difficulty of accessing this environment and the sheer number of unknown species makes the search for such compounds a slow and uncertain process. The impact of human activities on the Twilight Zone is an unknown that is only now coming into focus. Fishing fleets have begun to target mesopelagic fish for use in fish meal and omega-3 supplements, but the sustainability of this harvest is unknown. The reproductive rates and lifespans of these fish are so poorly understood that any removal could have unintended consequences for the entire ecosystem. Plastic pollution is also a growing concern, as microplastics have been found in the guts of Twilight Zone organisms from the surface to the deepest depths. The effects of these particles on the health and behavior of the animals are unknown, and the potential for them to be transported to the surface by migrating fish and then to the land by seabirds is a pathway that has not been quantified. The Twilight Zone, once thought to be pristine and remote, is now showing signs of human influence, and the full extent of that influence remains a mystery. The final unknown is the Twilight Zone's role in the evolution of life on Earth. This region is a living museum of ancient forms, with creatures that have persisted for hundreds of millions of years with little change. The coelacanth, a fish that was once thought to be extinct, is a resident of the Twilight Zone, and its biology offers clues to the transition from fish to land vertebrates. But many other relic species may exist, their evolutionary histories written in the dark waters that have remained stable for eons. The Twilight Zone holds the key to understanding how life adapts to extreme environments, and how the deep sea has shaped the evolution of the entire biosphere. Yet the most fundamental questions remain unanswered. How many species live there? How do they interact? And what will become of them in a changing world? The Twilight Zone, as a living archive of the unknown, continues to remind us that the ocean is not a place we have explored, but a place we have only begun to glimpse. The Twilight Zone is not merely a layer of the ocean. It is a boundary between two worlds, one bathed in sunlight and the other in perpetual night. This boundary is defined by the limits of light penetration, but it is also a frontier of knowledge, where every meter of depth reveals new questions. The very concept of the mesopelagic zone, as oceanographers call it, is a human construct imposed on a continuum that defies simple categorization. The creatures that live here do not recognize our labels, and their behaviors often seem to ignore the physical laws that govern the surface world. What we call the Twilight Zone is, in reality, a shifting mosaic of currents, temperatures, and chemical gradients that create invisible habitats within the water column. No 2 cubic meters of this zone are exactly alike, and the life within each parcel of water may be completely different from the one just a meter away. One of the most persistent unexplained phenomena in the Twilight Zone is the deep scattering layer, a dense aggregation of organisms that appears on sonar as a false bottom. This layer was first detected during World War II, when naval sonar operators noticed a phantom signal that rose to the surface at night and sank at dawn. For decades, scientists assumed this layer was composed of fish, but later sampling revealed that the scattering layer is actually a complex community of jellyfish, crustaceans, and small squids, with each species contributing to the acoustic signature in ways that are still not fully understood. The sheer density of this layer is staggering, with estimates suggesting that it contains more biomass than all the fish in the surface ocean combined. Yet we have only sampled a tiny fraction of the species that make up this layer, and many of the creatures collected are so fragile that they disintegrate before they can be studied. The deep scattering layer remains one of the largest biological structures on Earth, and its composition, behavior, and ecological role are largely unknown. The daily vertical migration of Twilight Zone organisms is another mystery that defies easy explanation. Every night, billions of tons of life rise from the depths to feed in the surface waters, and by dawn, they descend again to avoid the light. This is the largest animal migration on Earth, yet it is almost invisible to the human eye. The triggers for this migration are not fully understood, as some species seem to respond to light intensity, while others are influenced by the moon, currents, or even the presence of predators. The energy required for these vertical journeys is immense, and scientists are still trying to calculate how these creatures manage to sustain such a lifestyle. Some species, like the lanternfish, have specialized swim bladders that allow them to adjust their buoyancy, but others, such as the gelatinous zooplankton, seem to drift passively, suggesting that the migration is not a uniform behavior, but a chaotic dance of individual choices. The exact pathways of migration, the distances traveled, and the cues used by different species are all areas of active research, and no one has yet created a complete model of this nightly phenomenon. Bioluminescence in the Twilight Zone is perhaps the most visually spectacular unknown, with an estimated 90% of the creatures here capable of producing light. The light is used for a variety of purposes, including camouflage, predation, mating, and communication, but the specific signals of many species remain a mystery. Some animals produce complex patterns of flashes that appear to be a form of language, yet we have no dictionary to translate them. The firefly squid, Watacenia scintillans, creates a stunning display of blue light during its spawning season, but the purpose of this light show is still debated. In the deep sea, bioluminescent bursts can be triggered by turbulence, and some scientists believe that the entire water column may be a network of light signals that we are only beginning to decode. The evolutionary history of bioluminescence is also unclear, as the same biochemical pathways have evolved independently in multiple groups, suggesting that the ability to produce light is a powerful adaptation that has arisen many times. The Twilight Zone is a universe of light in the dark, and we are still learning to read its messages. The Twilight Zone plays a critical role in the Earth's carbon cycle, acting as a biological pump that moves carbon from the surface to the deep ocean. Phytoplankton in the sunlit zone absorb carbon dioxide, and when they die or are consumed, their remains sink into the Twilight Zone, where they are consumed by mesopelagic organisms. These creatures then respire carbon dioxide into the deep water, or they themselves are eaten by deeper predators. The efficiency of this carbon pump is poorly understood, and recent studies suggest that the Twilight Zone may actually store more carbon than previously thought, but the mechanisms are complex. Some carbon is transported in the form of fecal pellets, while other carbon is dissolved in the water column, and the fate of this carbon depends on the activity of microbes and the physical mixing of water masses. The Twilight Zone also contains large amounts of dissolved organic carbon, which is a vast reservoir of potential energy. But the microbial communities that break down this carbon are almost entirely unknown. As the ocean warms and acidifies, the carbon pump may be disrupted, and the consequences for the global climate are a major unknown. The number of species living in the Twilight Zone is a fundamental question that scientists cannot yet answer. Current estimates range from 10,000 to 1 million species, but these numbers are based on extrapolations from very limited sampling. Many of the creatures collected in nets are so soft-bodied that they are destroyed during capture, and the only way to study them is through advanced imaging techniques like remotely operated vehicles and submersibles. The gelatinous zooplankton, including jellyfish, comb jellies, and salps, are particularly difficult to study, as they often disintegrate in nets. Recent discoveries, such as the giant gelatinous siphonophore that can reach lengths of over 40 meters, suggest that the Twilight Zone is far more diverse than we ever imagined. The deep sea contains entire phyla that are only known from a handful of specimens, and it is possible that the Twilight Zone holds species that are not just new to science but represent entire new branches of the tree of life. The loss of such species before they are discovered is a tragedy that we cannot fully comprehend. The Twilight Zone is also a living museum of evolutionary history, with species that have remained essentially unchanged for millions of years. The coelacanth is the most famous example, but there are many others, such as the frilled shark, the vampire squid, and the goblin shark. These animals are often called living fossils, but that term is misleading, as they are not frozen in time, but have continued to evolve at a slow pace in a stable environment. The Twilight Zone has been a refuge for these ancient lineages, allowing them to survive mass extinctions that wiped out their relatives on the surface. The reasons for their persistence are not fully understood, but it likely involves the lack of competition, the stability of temperature and salinity, and the absence of major predators. The Twilight Zone may hold the key to understanding how life adapts to extreme environments and how the deep sea has shaped the evolution of the entire biosphere. Yet the most fundamental questions remain unanswered. How many species live there? How do they interact? And what will become of them in a changing world? The adaptations of Twilight Zone organisms are a testament to the power of evolution, but many of these adaptations are still unexplained. The giant eyes of the cockeye squid, which can be as large as dinner plates, are designed to detect the faintest traces of light, but the exact sensitivity of these eyes is unknown. The transparent bodies of many jellyfish, which make them almost invisible, are not just for camouflage but also serve as a way to avoid mechanical damage from the pressure of the deep. The ability of some fish to detect sound waves over long distances is crucial for communication, but the acoustic environment of the Twilight Zone is poorly mapped. The vampire squid, Vampiroteuthis infernalis, has a unique defense mechanism that uses bioluminescent particles to confuse predators, but the chemical composition of these particles has not been fully analyzed. The digestive systems of many Twilight Zone organisms are adapted to a diet of scarce and unpredictable food, but the metabolic rates of these creatures are astonishingly low, allowing them to survive for months without feeding. The Twilight Zone is a world of extreme ingenuity, and we are only scratching the surface of its secrets. Human influence on the Twilight Zone is a growing concern, and the full extent of that influence remains a mystery. Plastic pollution, once thought to be confined to the surface, has been found in the stomachs of deep-sea fish and in the tissues of gelatinous zooplankton. Chemical pollutants, including persistent organic pollutants, are transported to the deep sea by the sinking of particulate matter, and their effects on Twilight Zone organisms are unknown. Noise pollution from ships, submarines, and seismic surveys penetrates the ocean depths, and the impact of this noise on the hearing and behavior of mesopelagic animals is a subject of active research. Climate change is causing the ocean to warm and deoxygenate, and the Twilight Zone is particularly vulnerable because it is already oxygen poor in many regions. The deep scattering layer may shift in response to these changes, with unknown consequences for the entire ocean ecosystem. The Twilight Zone, once thought to be pristine and remote, is now showing signs of human influence, and the full extent of that influence remains a mystery. The Twilight Zone also holds the key to understanding the evolution of life on Earth. But this knowledge is fragmented. The transition from fish to land vertebrates is linked to the adaptations of lobe-finned fish like the coelacanth, but the exact sequence of evolutionary events is still debated. The Twilight Zone may have been a nursery for early vertebrates, providing a refuge from the harsh conditions of the surface during the early Paleozoic. The evolution of vision, pressure tolerance, and bioluminescence in the deep sea may have influenced the development of these traits in surface-dwelling animals. The Twilight Zone's role in the evolution of the entire biosphere is a vast and largely unexplored topic. The deep sea is not a separate world but a part of the same planet, and the connections between the surface and the depths are more intricate than we can imagine. The Twilight Zone is a living archive of the unknown, and it continues to remind us that the ocean is not a place we have explored, but a place we have only begun to glimpse. In the quiet darkness of the Twilight Zone, the unknown persists. Each dive, each sample, each sonar scan reveals more questions than answers. The nightly migration of billions of creatures is a silent symphony that we cannot hear, and the bioluminescent signals are a language we cannot read. The Twilight Zone is a vast library of evolutionary history, but most of its books remain unopened. The human desire to understand this world is driven by a curiosity that is as old as our species, but it is also driven by a growing urgency to protect what we do not yet know. The Twilight Zone is a frontier, not in the sense of a place to be conquered, but as a realm of wonder that we are privileged to glimpse. The mystery of the Twilight Zone is not a failure of science, but a reminder that the world is still full of wonders. The ocean, in its deepest layers, holds the secrets of the past, the present, and the future, and we are only beginning to listen. The sun is gone now. The last warm color has drained from the horizon, and the sky above the ocean becomes a deep, bruised blue. The water itself seems to hold on to the light for a moment longer, a faint silver glow that slowly fades into gray, then into something darker. There is no wind to speak of, only the gentle breathing of the sea, a soft rise and fall that is almost too slow to notice. The world has become quiet, not in the way of silence, but in the way of a held breath. Below the surface, the darkness is absolute. The water is cold and thick, and it stretches downward for miles, into a realm that no human eye can truly see. But something is stirring in that darkness. It begins as a whisper, a faint shift in the currents, a tremor that passes through the deep like a thought that has not yet been spoken. Billions of small things are waking. They have been waiting all day, hidden in the shadows of the middle depths, and now they feel the change. The light is gone. The time has come. They move without hesitation. Each tiny body rises, propelled by a motion that is older than any memory. They do not think about the surface, about the cold air waiting above, about the predators that will follow them. They simply rise. It is an instinct carved into their very existence, a pulse that beats in the darkness of every living cell. They do not know why they do this. They have never known. But they have always done it, and they will always do it, as long as the world turns and the sun sets and the night comes again. The first of them reach the shallower waters. They are so small that a single one would be invisible, a fleck of life lost in the immense blue. But together they form a living cloud, a vast and silent migration that fills the water column from the deepest shadows to the edge of the moonlit surface. Their numbers are beyond counting. They are more numerous than all the stars that will soon appear in the sky above. They are a river of life flowing upward, a river that has flowed every night for millions of years. The water around them grows slightly brighter as they rise. The light from the last traces of twilight filters down, and the tiny creatures catch it, reflecting it back in a soft, scattered glow. They look like a rain of stars falling upward, a reverse snowfall, a dream of light moving through the dark. The movements are unhurried, patient. There is no urgency in this ascent. It is a ritual, not a race. They rise because it is time, and time is the only force that matters here. Above them, the surface of the ocean is a mirror of the sky. The last streaks of orange have vanished, and the first stars are appearing, tiny pinpricks of ancient light. The water is calm, and the boundary between air and sea is almost invisible. The creatures continue their rise, passing through layers of water that have different temperatures, different densities, different smells. They do not notice any of this. They are driven by something deeper than sensation, something that lives in the very core of their being. The ocean is vast, and the creatures are many. They come from every direction, from every depth, rising together as if they are following a single command. There is no leader, no signal, no voice. Yet they move as one. The entire middle zone of the sea is transforming, becoming a living curtain that rises toward the night. The water itself seems to thicken with their presence, a slow, breathing mass of life that pulses upward with the rhythm of the earth. The creatures do not know that they are part of something ancient. They do not know that this migration has been happening for longer than the continents have taken their current shapes. They do not know that the oxygen they help produce, the carbon they carry, the nutrients they move, shape the very climate of the planet. They are simply rising. They are simply following the call of the darkness, the pull of the night, the quiet command that has been written into their existence since the first spark of life appeared in the primordial sea. The moon is not yet visible. The sky is darkening to a deep indigo, and the stars are becoming clearer, brighter. On the surface, the water is black, but beneath it, the living cloud continues to ascend. The creatures are now close to the top. They pause, hovering just below the thin skin of the sea, waiting. They do not break the surface. They do not need to. They have reached the place where the light of day cannot reach, where the darkness of the deep meets the darkness of the night. This is their destination, their home for the hours ahead. The water is full of them. The space between the surface and the depths is alive with movement, a slow, drifting dance that has no beginning and no end. Each creature is a tiny point of awareness, a fragment of life that knows only the rise and the fall, the light and the dark. They do not wonder about the world above. They do not dream of the sun. They exist in the moment, in the eternal present of the ocean, where time flows like the currents, slow and inevitable. The hours pass. The stars wheel overhead, and the moon rises, casting a pale glow across the water. The creatures drift in the shallows, feeding on the invisible particles of life that float in the darkness. They are part of a great cycle, a web of eating and being eaten, of living and dying that is as old as the sea itself. Yet there is no struggle in the way they move. There is only the gentle, ceaseless motion of life, the quiet persistence of beings that have no need for understanding. The night deepens. The creatures continue their slow wanderings, moving through the water with a grace that seems impossible for something so small. They are carried by the currents, but they also choose their own direction. They rise a little higher, then sink a little lower. They scatter and regroup. They are a fluid, living tapestry, woven from billions of individual threads, each one following the same ancient rhythm. The ocean is vast, and the darkness is deep. But the creatures are not alone. Other beings move among them, larger and faster, shadows that hunt in the night. The creatures sense them, perhaps, with a flicker of instinct that tells them to scatter, to dive, to hide. But they do not panic. They simply adjust, flowing around the danger, reforming their cloud in a different shape. The dance continues. The ocean is a place of constant motion, constant change, constant life. The first hint of light appears in the east. It is not yet dawn, only a faint paling of the black sky, a thread of gray that stretches along the horizon. The creatures sense it. something in them shifts, a subtle change that begins to pull them downward. The rise is over. The descent begins. They do not resist. They do not linger. The command is as clear as the one that brought them up, and they obey without thought. Slowly, gradually, they begin to sink. The water around them becomes darker as they leave the shallow light behind. They drift downward, not falling, but settling, like snowflakes through still air. The living cloud begins to disperse, to dissolve, to return to the deep. The light grows stronger. The sky turns from gray to rose, then to orange, then to gold. The sun is about to rise, but the creatures are already far below, descending into the shadows where the light cannot follow. They are returning to the middle zone, to the twilight world that is their home during the day. They will not see the sunrise. They will not feel the warmth. They will rest in the darkness, patient and still, waiting for the next evening when the call will come again. The descent is slow, unhurried. The creatures move downward in a great silent spiral, a living vortex that pulls them back into the depths. The water grows colder, heavier. The light fades to a dim blue, then to nothing. The creatures are alone again, surrounded by the vast empty darkness of the ocean, but they are not empty. They are filled with the memory of the night, with the taste of the surface, with the knowledge that they will rise again. The last of them sink below the reach of the sun. The water above them is clear, empty, as if the migration never happened. The ocean surface is calm, reflecting the golden light of the new day. The sky is bright, and the world above is waking. But below, in the silent depths, the creatures are settling into their rest. They are still, motionless, scattered across the great expanse of the middle water. They wait. The sun climbs higher. The hours pass. The creatures do not move. They are invisible, hidden, a secret that the ocean keeps from the daylight world. They are the guardians of the twilight, the keepers of the deep rhythm that pulses through the sea. They have no name, no story, no voice. They simply exist, as they have always existed, rising and falling with the turning of the earth. And so the cycle continues. The sun will set again. The darkness will return. The creatures will rise once more, billions of them, a living river flowing upward through the night. They will feed and drift and scatter, and then they will descend again before the dawn. They will do this tomorrow and the day after, and for as long as the ocean holds its breath and the stars keep their watch. They do not know why. They do not need to know. They rise because it is time. They descend because it is time. And the ocean, vast and silent, holds them all. And so the water holds its breath. The pressure deepens, a weight that presses against the stillness. But nothing moves. The light that once filtered down from the surface is now only a memory, a faint echo that lingers in the mind of the ocean. The creatures have become one with the darkness, their shapes dissolving into the endless blue-gray haze. They are not asleep, not awake, but suspended in a state that has no name, a waiting that stretches beyond time. The water around them is thick and cold, a liquid that seems to have forgotten the warmth of the sun. Tiny particles drift past, slow and aimless, like snow falling through a dream. They catch the last remnants of light, a faint shimmer that flickers and dies. The creatures do not turn to watch. They do not blink. Their eyes are open, but they see nothing, or perhaps they see everything. The slow pulse of the deep, the rhythm that has no beginning and no end. Above them, the sun continues its journey across the sky, but its light is a distant memory, a story told by the surface. The waves roll and crash, carrying the noise of the world, but none of it reaches down here. The silence is absolute, a living thing that wraps around each creature, holding them in place. They are not alone, but they are isolated, each one a separate point of existence in the vast, dark field. They do not touch. They do not speak. They simply are, like stones resting on the floor of a forgotten cathedral. The hours pass, and the water shifts, a slow current that moves without urgency. It carries the scent of the surface, the taste of sunlight and salt, but the creatures do not respond. They are anchored to the deep by an invisible thread, a connection that binds them to the rhythm of the earth. The current flows around them, over them, through them, but they remain still, patient, waiting for the signal that only they can hear. The light fades further, the last rays of the sun slipping below the horizon. Darkness spreads across the ocean, a blanket of black that swallows the sky. The creatures begin to stir, a subtle movement that is almost imperceptible. A fin twitches, a tail shifts, a body tilts, turning toward the surface. They do not rush. They do not hurry. The movement is slow, deliberate, like the turning of a great wheel. The water around them begins to glow, a faint blue light that pulses and fades, pulses and fades. It is not a signal, not a message, but a simple expression of the deep, a language that has no words. The creatures rise, not as individuals, but as a single, unified mass, a living cloud that ascends through the darkness. They do not push, they do not struggle, they simply let the water carry them, a gentle lift that pulls them upward. The light grows brighter as they rise, the blue fading to green, the green to a pale gold. The creatures do not stop. They continue their ascent, moving through layers of water that change in temperature and pressure. But they feel nothing. They are driven by something older than instinct, a force that lives in the very fabric of the sea. The surface approaches, a mirror that reflects the stars, but they do not break through. They stop just below the boundary, hovering in the thin layer between the deep and the sky. The night is vast and dark, but the creatures are invisible, hidden in the black water. They feed on the smallest particles, the tiny specks of life that drift in the current. They move slowly, their mouths opening and closing, a silent dance that has no sound. The water around them is alive, filled with the movement of 1,000 other beings, but they do not see them. They are focused on their own task, their own rhythm, their own place in the endless cycle. The hours pass, and the stars wheel overhead. The creatures drift, scatter, and regroup, a living river that flows through the night. They do not tire. They do not stop. They continue until the first hint of light appears on the horizon, a pale gray that grows and spreads. The creatures sense it, a change in the water, a shift in the darkness. They begin to descend, slowly at first, then faster, a cascade of bodies that falls back into the deep. The light grows stronger, and the creatures retreat, moving down through the layers of water, past the glowing blue, past the green, past the gold, until they reach the place where they began. They settle into the stillness, their bodies finding their old positions, their eyes closing, their fins folding. They are still again, motionless, scattered across the great expanse of the middle water. They wait. The sun climbs higher, and the water warms, but the creatures do not feel it. They are hidden, secret, a part of the deep that does not belong to the day. The ocean holds them, cradles them, a mother that never forgets her children. The water is their home, their world, their everything. They do not question it. They do not wonder. They simply exist, as they have always existed, rising and falling with the turning of the earth. The hours pass, and the light fades again. The sun sets, and the darkness returns. The creatures stir once more, rising from their rest, a living river that flows upward through the night. They feed, they drift, they scatter, and then they descend again before the dawn. They do this tomorrow and the day after, and for as long as the ocean holds its breath and the stars keep their watch. The water is deep, and the darkness is deep, and the creatures are deep within it. They are not seen, not heard, not known. They are the guardians of the twilight, the keepers of the deep rhythm that pulses through the sea. They have no name, no story, no voice. They simply exist, a part of the ocean that is older than memory, older than time, and the ocean, vast and silent, holds them all. The water moves, a slow, eternal breath, and the creatures move with it, rising and falling, rising and falling. They do not know why. They do not need to know. They rise because it is time. They descend because it is time. And the cycle continues, unbroken, unending, a rhythm that has no beginning and no end. The stars above are bright, and the water below is dark, and the creatures are suspended between them, a living bridge that connects the surface to the deep. They are not seen, but they are felt, a presence that lingers in the mind of the ocean. The water remembers them, holds them, carries them through the night. The dawn comes, and the light returns, and the creatures descend once more, slipping back into the shadows. They are gone, hidden, a secret that the ocean keeps from the daylight world. The surface is still, the waves are calm, and the sun climbs higher. The day is bright, and the world is awake. But below, in the silent depths, the creatures are settling into their rest. They are still motionless, scattered across the great expanse of the middle water. They wait. The sun climbs higher. The hours pass. The creatures do not move. They are invisible, hidden, a secret that the ocean keeps from the daylight world. They are the guardians of the twilight, the keepers of the deep rhythm that pulses through the sea. They have no name, no story, no voice. They simply exist as they have always existed, rising and falling with the turning of the earth. And so the cycle continues. The sun will set again, the darkness will return, the creatures will rise once more, billions of them, a living river flowing upward through the night. They will feed and drift and scatter, and then they will descend again before the dawn. They will do this tomorrow, and the day after, and for as long as the ocean holds its breath and the stars keep their watch. They do not know why. They do not need to know. They rise because it is time. They descend because it is time. And the ocean, vast and silent, holds them all. The water is deep, and the darkness is deep, and the creatures are deep within it. They are not seen, not heard, not known. They are a part of the ocean, a part of the rhythm, a part of the eternal cycle that has no end. The stars above are bright, and the water below is dark, and the creatures are suspended between them, a living bridge that connects the surface to the deep. They are not seen, but they are felt, a presence that lingers in the mind of the ocean. The water remembers them, holds them, carries them through the night. The dawn comes, and the light returns, and the creatures descend once more, slipping back into the shadows. They are gone, hidden, a secret that the ocean keeps from the daylight world. The surface is still, the waves are calm, and the sun climbs higher. The day is bright, and the world is awake. But below, in the silent depths, the creatures are settling into their rest. They are still motionless, scattered across the great expanse of the middle water. They wait. The sun climbs higher. The hours pass. The creatures do not move. They are invisible, hidden, a secret that the ocean keeps from the daylight world. They are the guardians of the twilight, the keepers of the deep rhythm that pulses through the sea. They have no name, no story, no voice. They simply exist as they have always existed, rising and falling with the turning of the earth. And so the cycle continues. The sun will set again, the darkness will return, the creatures will rise once more, billions of them, a living river flowing upward through the night. They will feed and drift and scatter, and then they will descend again before the dawn. They will do this tomorrow, and the day after, and for as long as the ocean holds its breath and the stars keep their watch. They do not know why. They do not need to know. They rise because it is time. They descend because it is time. And the ocean, vast and silent, holds them all. The water is deep, and the darkness is deep, and the creatures are deep within it. They are not seen, not heard, not known. They are a part of the ocean, a part of the rhythm, a part of the eternal cycle that has no end. The stars above are bright, and the water below is dark, and the creatures are suspended between them, a living bridge that connects the surface to the deep. They are not seen, but they are felt, a presence that lingers in the mind of the ocean. The water remembers them, holds them, carries them through the night. The dawn comes, and the light returns, and the creatures descend once more, slipping back into the shadows. They are gone, hidden, a secret that the ocean keeps from the daylight world. The surface is still, the waves are calm, and the sun climbs higher. The day is bright, and the world is awake. But below, in the silent depths, the creatures are settling into their rest. They are still motionless, scattered across the great expanse of the middle water. They wait. The sun climbs higher. The hours pass. The creatures do not move. They are invisible, hidden, a secret that the ocean keeps from the daylight world. They are the guardians of the twilight, the keepers of the deep rhythm that pulses through the sea. They have no name, no story, no voice. They simply exist as they have always existed, rising and falling with the turning of the earth, and so the cycle continues. The sun will set again, the darkness will return, the creatures will rise once more, billions of them, a living river flowing upward through the night. They will feed and drift and scatter, and then they will descend again before the dawn. They will do this tomorrow, and the day after, and for as long as the ocean holds its breath and the stars keep their watch. They do not know why. They do not need to know. They rise because it is time. They descend because it is time. And the ocean, vast and silent, holds them all. The water is deep, and the darkness is deep, and the creatures are deep within it. They are not seen, not heard, not known. They are a part of the ocean, a part of the rhythm, a part of the eternal cycle that has no end. The stars above are bright, and the water below is dark, and the creatures are suspended between them, a living bridge that connects the surface to the deep. They are not seen, but they are felt, a presence that lingers in the mind of the ocean. The water remembers them, holds them, carries them through the night. The dawn comes, and the light returns, and the creatures descend once more, slipping back into the shadows. They are gone, hidden, a secret that the ocean keeps from the daylight world. The surface is still, the waves are calm, and the sun climbs higher. The day is bright, and the world is awake. But below, in the silent depths, the creatures are settling into their rest. They are still motionless, scattered across the great expanse of the middle water. They wait. The sun climbs higher. The hours pass. The creatures do not move. They are invisible, hidden, a secret that the ocean keeps from the daylight world. They are the guardians of the twilight, the keepers of the deep rhythm that pulses through the sea. They have no name, no story, no voice. They simply exist as they have always existed, rising and falling with the turning of the earth, and so the cycle continues. The sun will set again, the darkness will return, the creatures will rise once more, billions of them, a living river flowing upward through the night. They will feed and drift and scatter, and then they will descend again before the dawn. They will do this tomorrow, and the day after, and for as long as the ocean holds its breath and the stars keep their watch. They do not know why. They do not need to know. They rise because it is time. They descend because it is time. And the ocean, vast and silent, holds them all. The water is deep, and the darkness is deep, and the creatures are deep within it. They are not seen, not heard, not known. They are a part of the ocean, a part of the rhythm, a part of the eternal cycle that has no end. The stars above are bright, and the water below is dark, and the creatures are suspended between them, a living bridge that connects the surface to the deep. They are not seen, but they are felt, a presence that lingers in the mind of the ocean. The water remembers them, holds them, carries them through the night. The dawn comes, and the light returns, and the creatures descend once more, slipping back into the shadows. They are gone, hidden, a secret that the ocean keeps from the daylight world. The surface is still, the waves are calm, and the sun climbs higher. The day is bright, and the world is awake. But below, in the silent depths, the creatures are settling into their rest. They are still motionless, scattered across the great expanse of the middle water. They wait. The sun climbs higher. The hours pass. The creatures do not move. They are invisible, hidden, a secret that the ocean keeps from the daylight world. They are the guardians of the twilight, the keepers of the deep rhythm that pulses through the sea. They have no name, no story, no voice. They simply exist as they have always existed, rising and falling with the turning of the earth, and so the cycle continues. The sun will set again, the darkness will return, the creatures will rise once more, billions of them, a living river flowing upward through the night. They will feed and drift and scatter, and then they will descend again before the dawn. They will do this tomorrow and the day after, and for as long as the ocean holds its breath and the stars keep their watch. They do not know why. They do not need to know. They rise because it is time. They descend because it is time. And the ocean, vast and silent, holds them all. The light that filters down from the surface is now a faint memory, a soft blue glow that barely reaches these depths. The water itself seems to hold its breath, a vast and patient stillness that stretches for miles in every direction. Tiny particles drift like snow, caught in the slow currents that move through this hidden world. They catch the last remnants of light, scattering it into 1,000 tiny sparks before they fade into the darkness. The creatures that were once so active, so alive with movement, have become part of this stillness. They hang suspended, their bodies angled just so, as if they are waiting for something that will never come. The ocean around them is a cathedral of shadow and silence, where the only sound is the low hum of the earth itself, a vibration felt rather than heard. The water presses in from all sides, a gentle weight that cradles every living thing in its embrace. The creatures do not resist this pressure. They have become one with it, their bodies adapted to the deep, their movements slow and deliberate. Some of them drift with their fins spread wide, like wings caught in a dream of flight. Others curl into themselves, forming spheres of flesh and bone that float like tiny moons in the darkness. There is no urgency here, no rush to feed or flee. The deep has its own rhythm, a pulse that beats once every day and night, and these creatures are its faithful servants. The darkness deepens as the last rays of the sun disappear from the world above. The ocean above becomes a mirror of the night sky, reflecting the stars that are now beginning to appear. But here, in the middle water, there is no reflection. There is only the blackness, a blackness so complete that it feels like a solid thing. The creatures that live here have learned to navigate this void without eyes, using other senses that are beyond the understanding of those who live in the light. They feel the vibrations of the water, the subtle changes in temperature, the faint chemical trails that tell them where their prey might be hiding. They are not blind. They see in ways that are not seeing, with a perception that is woven into the very fabric of their being. The hours pass, and the stillness deepens. The creatures remain motionless, their bodies barely visible against the blackness. They are like ghosts, like shadows that have taken on a temporary form. Their gills open and close in a slow, rhythmic dance, drawing oxygen from the water that surrounds them. Their hearts beat slowly, conserving energy for the long wait ahead. Some of them have bioluminescent patches that flicker occasionally, brief pulses of light that travel through the water like whispers. These lights are not for communication. They are simply a part of the creature, a natural expression of its existence, like the glow of a firefly on a summer night. But here, in the deep, there is no summer. There is only the eternal cold, the eternal dark. The currents shift, carrying the creatures gently, imperceptibly, across the great expanse of the middle water. They do not fight this movement. They allow themselves to be carried, their bodies turning with the flow, their fins adjusting to the subtle changes in direction. They are like leaves on a river, drifting without purpose, without destination. But they are not lost. They know where they are. They have always known. The ocean is their home, their only home, and they have memorized its every nuance, its every hidden path. They ride the currents as a bird rides the wind, trusting in the unseen forces that guide them. The water grows colder as the night deepens. The temperature drops by a fraction of a degree, a change that is imperceptible to human senses, but that every creature here feels in its bones. The cold seeps into their bodies, slowing their metabolism, slowing their thoughts. They become even more still, their bodies sinking ever so slightly in the water. Some of them begin to release tiny bubbles from their mouths, bubbles that rise slowly, catching the faint light from the surface before they pop and disappear. The bubbles are a sign of life, a reminder that even in this deep stillness there is breath, there is existence. The stars above have reached their zenith, 1,000 points of light that the ocean mirrors in its own way. The surface of the sea is calm, a sheet of glass that reflects the heavens with perfect clarity. But here, in the depths, the light from those stars does not reach. The creatures are blind to the sky, blind to the world above. They know only the water, the pressure, the cold. They know only the rhythm of their own bodies, the slow beat of their hearts, the gentle flow of blood through their veins. They are isolated, each one alone in its own pocket of darkness, but they are not lonely. Loneliness is a concept that belongs to the surface world, a world of names and stories and memories. Here there is only the present, the eternal now, the endless moment of being. The hours pass, and the creatures begin to stir. It is a subtle change, a barely perceptible shift in their posture. Their fins move, just a little, as if testing the water. Their eyes, if they have eyes, open wider, catching the faintest traces of light. The deep rhythm is calling them again, a pulse that has been beating since the beginning of time. They respond to this call without thought, without hesitation. They rise. They rise not because they are hungry, not because they are following a schedule, but because the ocean itself is telling them it is time. The water around them seems to thicken, to press against them, urging them upward. The darkness yields, just slightly, as they begin their ascent. The ascent is slow, a gradual climb through layers of water that grow warmer, lighter, more alive. The creatures move in unison, a silent army of shadows that stretches from the abyss to the surface. They do not speak. They do not need to. Their movements are synchronized by something deeper than language, something that connects them all in a single flowing river of life. The water around them begins to shimmer with bioluminescence, a gentle glow that pulses with the rhythm of their ascent. It is as if the ocean itself is lighting their way, marking their path through the darkness. The light is soft, blue, ethereal, like the memory of a dream. It does not illuminate the creatures. It only hints at their presence, a suggestion of movement in the deep. The first hints of dawn are beginning to touch the surface. The sky above is turning from black to gray, the stars fading one by one. The creatures feel this change, even through the miles of water that separate them from the surface. They feel the light, not with their eyes, but with their skin, with the cells that have been attuned to the rhythms of the sun for millions of years. They do not stop. They continue their ascent, drawn by the promise of the dark that will return, the cycle that will never end. They are the messengers of the deep, the bridge between the light and the dark, the day and the night. The water above them is growing brighter, the blue glow of the Twilight Zone giving way to the green of the sunlit waters. The creatures are now close to the surface, close enough to feel the warmth of the sun, the first rays of the new day. They do not pause. They do not break the surface. They stop just below it, a vast cloud of life that hovers in the boundary between the known and the unknown. They are the swimmers of the shadow, the dancers of the middle water. They are the ones who never see the sky, who never feel the breeze, who never know the world above. But they are no less real, no less alive, no less a part of this great spinning planet. The sun rises, and the light floods the upper waters. The creatures begin to descend, slowly, reluctantly, as if they are saying goodbye to something they cannot name. They sink back into the deep, back into the darkness, back into the stillness that is their true home. The water closes over them, and they are gone. The ocean above is calm, serene, untouched by the vast migration that has just taken place. The surface reflects the blue of the sky, the white of the clouds, the golden light of the sun. No one sees the creatures. No one knows they are there. They are a secret, a mystery, a hidden world that exists beneath the waves. The hours pass and the sun climbs higher. The creatures settle into their rest again, their bodies drifting, their minds empty. They are still, motionless, scattered across the great expanse of the middle water. The darkness holds them, cradles them, protects them. They wait. They do not know what they are waiting for. They do not need to know. They wait because that is what they do. They wait because the ocean has asked them to wait. And so they wait, suspended in the deep, a silent chorus of life that hums with the pulse of the planet. The sun will set again, the darkness will return, the creatures will rise once more, and the cycle will continue. It has always been this way. It will always be this way. And the ocean, vast and silent, holds them all.